Hello, sir.
Yeah.
Is it possible to play the video, sir?
Yeah. Actually, right now it is. Let me see. When I say start video, it says okay. It lets me start. That's good. The next thing is recording. So if you go to my name on the more and you click more, then there it will tell you to allow to record. I cannot do that, but you can do that. Go to my name
Okay,
and
sir.
then go more and then say allow recording.
It's already been allowed, sir.
It's already being allowed. Okay. Can you do the same on the second one, please? Same thing.
Sir, it has been
I
enabled
I
in
have
both.
to. It has been enabled on both. Okay. Let me
Yes, sir.
see.
Okay, sir.
Okay. So now, um, where is Zoom? Yeah. Thank you. I can see it's being allowed on both. All right. So now the next thing I'm going to do is to share my screen. You can continue sharing your screen, but I just want to try out my screen, and then basically we can switch back if you need to. So my screen is right here. Come on, going.
Sir, it's visible.
Okay, looks good. Yeah. I'll have to rearrange my photo position so that it is not overlapping um, any of the slide text. So I'm going to do that. That's how I record my lectures every day. All right. The Zoom actually puts the picture somewhere which may not be the best position. Okay, so I'm all set on that computer. It is recording, and so I will leave that alone, and then I can come back to my main computer. Actually, I have to stop the sound. I don't know. I think this is probably fine. Check my muting. Okay. 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 All right, it's recording. No problem. Now I will come back to this screen. And okay, there is a problem. Hold on. How do I? Hello. Sorry. This one has to be connected. I'm sorry.
No, sir.
I want to connect it right here. Okay. Hello. Now start video. View exit full screen. Okay. All right. Now that's done. Go back to full screen. Okay. That's perfect. Now I come back to this screen. Okay. All right. Okay. So actually I'm all set from my side. Do you want to go back to your screen or do you want to leave this screen on?
We can keep it the same screen, sir. It's okay.
Okay. All right. Thank you. And then Professor Thampi, is he there? I mean, like, can I talk to him? I mean, can he unmute himself and then I can
Yes,
talk to
yes.
him?
Good morning, Professor.
Yeah.
Good morning.
He's
Okay.
online, sir.
So you said something about, yeah, thank you. Thank you. I can hear him.
Okay. Okay.
So you said something about inaugurating in the morning. What
Yeah.
you want me to just say welcome everyone or say something more?
Just you can speak about your research and about the theme of the summit, and then inaugurate.
Okay, hearing. I think it's better to do it
Yeah.
on the chat. Can you say on the chat because it's not very clear to me. So let's see. Where is the chat on my case? Chat.
My
And you
voice
can
is
just
not
give a
clear.
private chat.
Yeah, I have a cold now.
I know that's okay. But basically,
Mm.
well, this is a season for cold. Actually, you believe it or not, we have 5 inches of snow in our driveway.
Okay.
And oh boy, this is what a weather. All right. So can you say something on the chat box and just privately to me? I mean, like that way, it's okay. What do you exactly want me to do? Let's see. So all panelists, Sambu. Okay, so I can just connect to you and I can say,
No, sir. Let me start.
Yeah.
Morning, all. We are extremely delighted to welcome you to the Day 2 event of DX21 Digital Transformation Summit, organized by the Kerala University of Digital Sciences, Innovation and Technology, KUDSIT, in association with IITMK, ACM Trivandrum Professional Chapter, KDIS, IEEE ComSoc, and GTEC. DX21 aims to cover the latest trends and vital aspects of digital transformation and increase the exposure to disruptive technologies and achievements pertaining to Industry 4.0. This summit provides a golden opportunity to connect together, integrate knowledge, and share ideas on digital transformation via Industry 4.0. Day 2 of the event is dealing with the theme Digital Transformation, Opportunities and Challenges, which will be handled by well-tailored and handpicked collection of eminent speakers from renowned institutions in and outside India. Hope all of you would benefit from the scholarly sessions. Wishing you all a wonderful day ahead. Today's first session is handled by Dr. Raj Jain. The title of the talk is Extending Blockchain with AI for Risk Management. Dr. Raj Jain is the Barbara J. and Jerome R. Cox Jr. Professor of Computer Science and Engineering at Washington University in St. Louis. Previously, he was one of the co-founders of Nina Networks Incorporated, a next-generation telecommunication system company in San Jose, CA. Dr. Jain has a PhD in Applied Mathematics and Computer Science from Harvard University. He is a fellow of IEEE, ACM, AAAS, and Academy of Science, St. Louis. He is the recipient of 2017 ACM Sitcom Award, 2015 AA Michelson Award from Computer Measurement Group, and numerous other awards. With 34,000 plus citations, according to Google Scholar, he is one of the most cited authors in computer science. On behalf of KUDSIT, we welcome you, sir.
Thank you. Thank you. And it's a pleasure actually to speak. Somebody has muted his microphone on, so I have to unmute everyone. Or maybe you can unmute everyone. Mute everyone. Okay, so it's a pleasure to speak at this summit. And this summit is, as you know, is very timely. The topic of the summit is digital sciences, right? A digital transformation. And I have been in networking for about 1978 to now. I was just counting 48 years, maybe 78. Yeah, 78, 22 plus 20, 42 years. And we have been talking about virtualization and digital transformation for at least 30 years. However, this year is very special. The COVID has made everyone digital. Everything is digital now. Everything is basically, from this talk itself, which I would have had difficulty if I were to give the talk 2 years ago. But now everything is, basically virtual and digital. And so appropriate time to get into this. And let's go on to my topic, which is extending blockchain with AI for risk management. And by the way, like my other talks, this talk is also online right now. You can just scan this and then download it right now, or at the end of the talk also I present the same QR code. And on every slide there is a URL where you can go and download it anytime. All right, so with that, we move on to the what we are going to talk about. First, we are going to talk about what are the strengths of blockchains, what are the weaknesses of blockchain, and how we extend it, and we call it knowledge chain. And so, first of all, most of you know what is a blockchain, and most of you associate that with Bitcoin. You know, Satoshi Nakamoto invented the Bitcoin, shown here. He used the blockchain to make it decentralized. So the key technology behind Bitcoin, by the way, this Bitcoin picture is fake because there is no such thing that you can hold in the hand. Bitcoin is virtual, right? But still, people like to use this picture to show that this is a Bitcoin. Bitcoin cannot be seen. So anyway, so he invented Bitcoin, and he really solved many problems of the time. In 2008, there were other virtual currencies. There were many attempts before that. They all failed, but Bitcoin survived. And it is surprising that 2008 to 2020, 12 years later, it is still doing well. In fact, today's news is that the price is 48,000 per dollars per Bitcoin. It used to be 443 just a few years ago, and when it was started, it was nothing. All right, and this is one of the best investment, 151% per year. However, having said that, I do not invest in Bitcoins, and I would not recommend that you do, because it's basically, I mean, very risky. Anyway, moving on to the blockchain. So after Bitcoin became successful, people started looking into what is it makes it very strong, what is it makes it useful, and they found that the key technology is the blockchain. And they said that that is not just good for Bitcoin, it is good for many things. In particular, it allows two complete strangers to enter into a smart contract without a trusted third party. And so this whole talk is about blockchains, not about Bitcoin. Sorry. So I'm not going to talk about investments or Bitcoins or anything. This is about blockchain, which is just the technology behind the Bitcoin. And the best way to introduce blockchain is to introduce how the weddings are done. There are two ways to get wedded. Basically, if you want to marry someone, there are two ways. On the left, you go to an office, sign on a register, and you get married. You get a certificate, and you can show it to everyone and prove that you are married. On the right, there is another method, which is that you just invite all your town people, all your relatives, all your friends, and you get married. You don't get a certificate, but you are married. If somebody says, yeah, I saw you, you got married that time. So the question is, which is the better way of getting married? Basically think about it right now in this virtual format. I don't think I can expect answers from you, but just think about it. And I will give you the answer. So my son just got married last month using this method on the left. And I got married the right way, actually using this method. Now you will say why that is the right way? Because this method is decentralized. This method is centralized. And centralized things have single point of failure. That register is a single point of failure. If somebody hacks the register, now you're not married to Kamala, you are married to somebody else, named Bimla. Who knows who gets married to, because register says so. And it is easy to hack. And we will see that in real life, that's what exactly happens. Not for the wedding. Nobody wants to make a fake wedding, but for the other things where we use a register. And here there is no register, single register. Actually, everyone is a register. Everyone has a brain. Everybody remembers that you got married. So if somebody wants to fake it or change it or do something, they will have to go to 100 people, and in some cases 1,000 people, 5,000 people, and say, well, do you really think this guy got married to this person? And so this is fault tolerant. There is no monopoly and very difficult to hack. So this is where the world is going right now. Decentralized. That's the keyword. And I will show you why. So where are the examples of centralized systems? Banks are centralized systems. You put the money into the bank and the bank can actually hack it. Bank can go out of business and your money is gone. City records, wedding registry was an example, but property ownership, you can give some money to the city guy and he will make the property owned by somebody else. It is no longer your house. Networks, certificate authorities. Certificate authorities give you all the certification that you are Raj Jain, and then when they get hacked, everybody can become a Raj Jain. All right, and this has happened. DNS, some people can hack DNS and say, well, I am google.com, and then all the traffic goes to that particular website. Anyway, so in all these cases, there is a central third party to be trusted. And central party maintains a very large database, and that's why the hackers like it. They go there to the central place. They don't want to go to 1,000 people. They just want to go to one place. Central party may be hacked and affects millions. And central party is a single point of failure. It can malfunction or it can be bribed. So that's why people are getting away from that centralization and becoming decentralization. So what we did was, when we got into this few years ago, we said, okay, so let's find out what can we do for research in this area. And basically one mantra for doing research in any area is to find what are the latest technologies and how to apply to this thing. So the latest technologies are AI, of course, And then, you can count your own, whatever you are interested in, and then you want to apply it to whatever you're working on. And in this case, if you want to work on blockchain, we said, how can we apply to this? And then, so we said, okay, what is good about blockchain? First thing, it is distributed. Second thing, it is decentralized. Third thing, it is trustless. What that means is that you don't need to trust anybody. You see, in this place where 1,000 people have registered your wedding, you don't have to trust them that they are not your enemies. You can call anybody, they can come to the wedding and they can lie, but other people will still be there, right? So there is not single point of trust. Cryptographic security, and security wise, it is very strong right now. At least you cannot break it. Is one of the latest technologies, and someday you might be able to break it, but right now not. And non-repudiation guarantee. What that means is that everything is signed by somebody, and you can prove that signature in the court of law that this was done. Although with some of these things, it is difficult to say that this is your name, because Bitcoin is anonymous, and so I can put my name whatever I want to, and then I can sign it. All right, as long as I keep that name, I can prove that this is my signature or this is the money I received. But if I can change the name, that means people will have to basically find out the real name and the physical name and the virtual name. All right, okay, so we got thinking. And we found out, oh yeah, there are some problems with the blockchains that we can, then we absolutely, the rest of the talk we will solve about. First thing is, in the blockchain, only facts are recorded. So you can record that Alice is married to Bob, that Alice gave 20 coins to Bob, that Alice signed a contract with Bob to pay 10 coins for 1 kg of XX, whatever that XX is. So this last example is example of a contract, and that is where the blockchain is being used for right now. So it is good for facts, and it has therefore binary validity. So all transactions on the block are either that are committed are valid. So what happens is you say whatever you want to say. You say, I want to give 10 coins to Bob, and then you broadcast it to the world, and a lot of people will listen to it, and then they will verify that you do have 10 coins. And if they verify that you do have 10 coins, then they will write it on the ledger, which is the blockchain. And if enough people write the same way, then you really have given the 10 coins, and then now Bob can spend those 10 coins. So all transactions are recorded on the blocks that are committed are valid, so that those transactions are valid. Those not committed are old and invalid. So if nobody likes your transaction because you didn't sign it properly, or because you really didn't have 10 coins, then those are invalid. So recording is binary 0 or 1. And deterministic events only. You cannot record that I'm 90% sure that Alice gave 20 coins to Bob. So if you're not sure about something, you cannot record it on the Bitcoin. You cannot say, well, I'm 90% sure that Alice is married to Bob. That is not something that you can record right now. And so we said, okay, there we go. I'm a probability theory person, so why not apply that? Then we said the second thing is that it is a data storage. So the blockchain actually is not a smart thing. It is simply a storage, and we have done that in computer science many times. We started with virtual memories with the storage, then we went into virtual computing, virtual networking, and so on and so forth. So I remember all that trend, and I said, okay, how can we move from storage, await storage, to something else? Second thing is, everything is deterministic. So of course, I want to make it non-deterministic. And so we need to move from data to knowledge. Now, we don't really like data too much. We like knowledge. And so we are in the big data and machine learning age. So why don't we somehow apply that to this? And the real life is probabilistic. It is not deterministic. I mean, I really don't know what will happen to me tomorrow or anything about tomorrow. And every decision we make are probabilistic decisions, and most decisions have some risk. So all of these things are not possible by the current blockchain. So what are the things that, decisions are that have risk? All the decisions that we make, for example, when you sell an insurance, you are assuming that this person will not die early, and therefore you will get the money to keep. And when you buy insurance, you just assume the opposite, that I might die, and then therefore let me, get this insurance so that my family will, survive. When you sell a stock, you feel that it will go down, and when you buy a stock, you feel that it will go up.
and you download a software on your computer, you don't know, you feel that it will be good for you, but you don't know that this is virus. When you update your computer with any Microsoft Windows, you don't know whether it will run tomorrow. You just assume that it will run tomorrow, but sometimes it doesn't. And you marry someone, of course, you're taking a risk for life. And I've been happily married for 50 years. So, I mean, I can't complain, but you know, some people can. All right. So our goal was to change the chain from deterministic to probabilistic, to chain from storage to computation. So we do some computation, we added some computation. And instead of data, we added some knowledge. And basically, now you can use it for decision making. It is similar to where the rest of the world is going. Google no longer does the data search. Let me tell you, when you want to do something, you go to Google and Google tells you what you're thinking. Believe it or not, you just write, you know, blockchain. I just write a block and will say blockchain. You know, how does it know? It just, you know, knows. Similarly, so it suggests using AI, and a knowledge chain, a similar knowledge chain would be much more useful than just, you know, telling you exactly what is there, right? So there have been 3 generations of blockchain. First, the coin, Bitcoin, which is old. Then smart contracts, then faster processing, and many different consensus methods. We will not go into that. And then now we hope that the 4.0 will be ours, which is blockchain with AI and smart decisions. Okay. And so this is what we have done. The users broadcast signed transaction. This is the old method. Right now, I'm just going to explain how the blockchain works. Users broadcast signed transactions, which could be a contract, which could be just a transaction. I give you money, I know, or I want to record this thing. So these are all the transactions from different users. Then there are some nodes which are called mining nodes, and they validate these transactions because each transaction is signed. So they verify the signature, and then they create a block. This is why I call it blockchain, because not each transaction, they take hundreds of transactions and then put into a block, and that block points to the previous block, to the previous block, to the previous block. And then, you know, basically what will happen is many miners will produce many blocks, and they will point to different places in the chain. At the end of the day, the one that is followed by most other block creators is the one that wins. So the one that the chain that becomes the longest wins, and all other blocks are thrown out. Only the longest chain survives, and that if we do it every 6 blocks, so I mean, not every 6 blocks, every block, when it becomes longer than 6 blocks, the chain becomes longer than 6 blocks, then we throw away the rest. And so it takes about 1 hour right now on Bitcoin, because blocks are made every 10 minutes, and you have to wait at least 1 hour before coin becomes yours. All right. The point I wanted to bring was, I'm not going into Bitcoin. The point I wanted to bring was that the more mining nodes there are, the better it is. The more users there are, the better it is. And therefore, if you have only 2 miners, the blockchain is not useful. All right. If you have only 2 users, then you don't need blockchain. All right. If there are only 2 banks in the world, why do we need blockchain? You know, that's already centralized and so on and so forth. So blockchain is useful when you have lots of these things. And that's what the dream of Nakamoto was, that there'll be thousands of miners. Although that dream has failed, there are only 3 miners left in the world, all of them in China. And therefore, it is kind of a myth that Bitcoin is decentralized. Anyway, I'm not going to go into Bitcoin too much, but basically, let's going to assume that the blockchain process is decentralized, lots of miners. And we made a very minor change. We said that you can broadcast transactions, and they do not have to be exact facts. You can broadcast your opinion. I think it will rain tomorrow, or I think that the IBM stock will go up tomorrow. Whatever your opinion, you can broadcast. You can even put a probability and say that I'm 90% sure that will go up and 10% chance will go down. And anybody can say that, and lots of people can say that. And then the mining nodes, they validate the transaction, but they also do this AI stuff. And they figure out that, okay, so based upon all these 1,000 people, I think the probability that it will go up tomorrow is 99%. All right. Or they can say something else. They don't have to say exactly that simply. They could just say that here is the probability distribution of what will happen tomorrow. And then the blockchain nodes will validate the block, and whoever's blocks become sick, whatever length, then they win, and everything else, fails. So everything else is same, except that now we allow you to say whatever you want to say. There is no limitation that it has to be truth. You can say false things too. And you can put a probabilistic thing, you can guess things, you can say, I guess that Bob is married to Alice, who knows. And you put your probability stuff. All right. And then the key problem is that there is a machine learning algorithm or something required to take all this information or this data and to convert into knowledge. And that's a tough one, right? But I'm going to leave that alone for right now. But basically, that is the whole thing we are going to do, is we are going to take lots of data, and then we can summarize it using some AI thing. And then we can basically get some knowledge out of it. And here's an example. So, I mean, the summary doesn't have to be AI. It could be a simple mean, median, moment, or whatever. It could be any data mining algorithm, and it could be machine learning algorithm. So we did for our experiments, of course, our goal is simply to publish papers, not too much more than that. I'm a professor. So basically what we did was we gave a problem to thousands of people. And of course, we don't have thousands of people. So what we did was we gave it to thousands of agents in the computer, which used, each of them randomly picked something to generate, and we gave them some AI algorithm that they randomly picked to generate their opinion. And then they broadcast the opinion, and then we summarized it using a very simple function. But really what we need to do is use more sophisticated ones. Here's the result. Those agents that selected random forest, they were 99.05% accurate. Decision tree were 98%, logistic 9%. But when we combined everything, the whole thing is much better than any one of them. And this is a well-known fact. Distributed decision making is better than any individual decisions. Whatever you can decide based upon your own knowledge is always limiting. But if you ask 5 people and then do it, it is much better. Okay. If you ask 5,000 people and then do it, it is much better. If you can somehow do that, right? So what it is this is what we call knowledge chain. And to summarize, basically a blockchain is a distributed ledger. So I have shown this in picture here. This is a ledger on which you write whatever you want to write. And this is distributed. So I have shown the picture of the world. This doesn't exist on a single register. This is a ledger which extends worldwide, and anywhere people can write on it, and anywhere people can read it. And so this is free for all kind of thing. And so it is a big database. And what we have done is, and actually initially we called it probabilistic blockchain, but now we call it knowledge chain. So it has a big database, and that can be mined to become knowledge. So the database is basically who bought, who sold, what quantity, what price, and Fidelity has a big database. All right. And so that is not what is interested in. What we are interested in, where the market is going. Somehow using that database, can we find that, whether we should buy, sell, or hold. And now if we are not in the stock market, then the question is, these are the common things that we can decide using this method. First is this a fake news? We have had lots of fake news recently over the last 4 years. And so where is it coming from? Who is starting it? Who is fake? Who is not fake? And then both sides will argue that no, this other side is fake. Whether it is spam, same thing happens. You say it is a spam, somebody says, no, this is the information. It is a fraud. For somebody it is a fraud, for others it is not. And so basically, there are many examples of this. And the summary is that what we have come to is what we call crowdsourced knowledge. We are doing crowdsource financing, crowdsource, many things you can do crowdsource, and now you can do crowdsource knowledge. And crowdsource knowledge or crowdsource decision, when you want to make a decision, you send out the question on the blockchain. And a lot of people, everybody can read that question because it is open, and everybody can respond to it with whatever way they want to identify. And then they are summarized. And then basically there is a lot of other questions. So when you start making decisions and you start taking risk, then it is not just simply summarizing something. You have to summarize so that the risk is minimized. So there are lots of other questions come in, which we'll talk about in a minute, but not too much. So the application examples. So where can we use this thing? We can use it for spam detection, email, IP addresses, cloud providers, source, public IP. So everybody who thinks something is spam writes it on the blockchain, and we make a note of what email, IP address it came from, which cloud provider it came from, what is the source, what is the public IP, and so on and so forth. And somebody can mine all that up and put the answer very fast, so other people will benefit. Intrusion attacks, same thing. If you feel there is an intrusion or attack, you put all the information in the blockchain, and you can anonymously share the attack information, and then of course people will benefit from it. Gray domains, the domains which are not legit. Reliability issues with recent software updates. If a lot of people got hacked, not hacked, actually crashed with the recent update of some software, then they list it on the blockchain and we can mine it. Error reliability statistics of the IoT devices. Now, IoT devices come in millions and they fail in millions. They fail very often. And so we really need to know what is happening in certain area with certain devices, with certain manufacturer, with certain whatever. It can be used. And virus in the software. And right now with COVID also, you can use it, for getting any information about any vaccine or any side effects or any other thing, whether masks are useful. You can do all that with this kind of distributed database. Now the issues to resolve. So there are several issues and we are working on them one by one. First is the summary function. So we are basically summary function, there is no general answer. I think basically for every problem there is a correct answer or there is a way, and there are so many AI algorithms nowadays, and then people, once they start using it, they will say that, okay, I think this one works better than the other in this kind of application. Then overhead of consensus mechanism. This is a big rat hole, and I will not go into that, whether proof of work is good or proof of stake is good or proof of that is good. How do you do that? So much electricity, should I waste all that electricity? Should I not waste? It turns out for my problem, this is not an issue. I don't dictate that you use one or the other. You can use any way to come to a consensus. Okay. Reputation. This is the big factor. So people can lie, so we have to somehow detect the liars, and we are working on that. So we have published 2 papers on that. And so we keep dynamically some statistics on who said what and when and how often they change and so on and so forth, and how they cannot just simply adopt a new identity and come on, because identity is a dynamic identity in blockchains, in a real blockchain. Now you could have some other blockchains which are very popular nowadays, private blockchains, are restricted blockchains and all that, where you have to identify yourself, you have to produce your birth certificate, and before you can write anything. And so those have different ones, right? But right now we are considering really open blockchains, and this applies, by the way, to private blockchains, but we are not considering that because they are trending towards centralization. So that brings me to the end of my talk, and the 5 key messages are that the blockchains provide an immutable, which you cannot change, secure, and a distributed database. And that's the problem. The last word is the problem. We are not interested in data or the database. So we have had 3 generations, cryptocurrency to smart contract to faster performance. I think the 4th generation, which will be more with AI, will be the right one, or will be the new one, will provide, and so we don't really want to make it only a storage. We want to make it knowledge. We want to somehow put computation in this whole process, and so we call that knowledge chain. And then we have some papers, and that's the end of this talk. So if there are any questions, I still have 2 minutes or 1 minute left. I don't know, but you can ask or send the questions to the panelists. They can send to me, or you can send to me, whichever way, on the chat box only. No unmuting of anybody. So please write a question. If not, basically I'm done. And this is the QR code. You can still scan it with your phone, or you can just take a picture of this whole slide with your phone and scan it later when you have a QR code, or you can just write down with your hand this URL, which will take you to exactly to this talk for DX21, or you can just remember my name, rajjain.com, and when you go there, just search for this talk. Just search for DX21 maybe, and Google will help you to get to this talk. Any questions?
Thank you, sir. Thank you for your informative session explaining even the basic concepts of blockchain in a very simple way. So we have a question.
Yeah, I can see the.
From
Go ahead. You can either you can say the question or you can say the question. That's fine. Yeah, go ahead.
How is this different from ensemble learning or decision fusion with agents sitting on blockchain?
Yes, exactly. That's what it is. Is that the ensemble learning with agents sitting on the blockchain? That's exactly our idea, by the way. I don't think I saw that idea before we came up with this. We actually patented it. Although I'm not enforcing that patent, I have not really done. We applied for the patent back in 2018, and I think the university is probably whatever probably the university is doing, but I am in interest of seeing it applied. So yes, I don't know. I mean, I would say yes. If you want to say that I'm applying AI to with agents sitting on blockchain, that's exactly fine. The main thing is, though, I mean, I would say that the agents really, I don't know, we have to define agents. In my case, I call the people who are making the forecast or making the opinions, I call them agents, and the people who are doing the mining, they are the one who are applying the AI. So they are doing ensemble learning, you know, not the people who are, so anybody can say that the stock market will go up tomorrow. In our case, they're not doing, and they could be using AI or they could do whatever. But really the ensemble learning is being done by the miners. And I don't want to use the word miners because there are blockchains. Miners is the word which applies to Bitcoin blockchain. And then people say, oh, well, I have this other blockchain which doesn't have miner. Okay, all right. So whoever summarizes this whole thing is the one that uses this ensemble learning. Any other question? And that was a good question. Thank you.
Any other questions from the audience side? You can post it on the Q&A.
All right. I think I really had a good time talking about this, and all the papers are on our website, and this talk also, the slides are already on the website, and I have recorded, the university has recorded, and I will post it on my website by tomorrow. And so exactly, if you go to the same URL, you will find a recording of this. If you want to share with anybody else, that's fine. Okay, thank you.
Thank you, sir. Thank you for your valuable time.
Yeah, thank you.
Our next session is handled by Dr. Mukesh Mohania. Our next session is handled by Dr. Mukesh Mohania on the topic Technologies for Industry 4.0 Revolution. Dr. Mukesh Mohania is a professor at the Department of Computer Science and Engineering, Indraprastha Institute of Information Technology, Delhi. He was a faculty member in University of South Australia and West Michigan University from 1995 to 2001, and then worked at IBM Research, both India and Australia, for more than 18 years as distinguished engineer. His research interests are on information integration, master data management, AI-based entity analytics, big data analytics and applications, and blockchain data management. He has received several awards within IBM, such as Best of IBM, Outstanding Innovation Award, Outstanding Technical Achievement Award, and many more. He has published more than 120 research papers in reputed international conferences and journals and has more than 50 granted patents. He has held several visible positions in academia and professional activities and is a recipient of the HCM Outstanding Service Award and the IEEE Meritorious Award. On behalf of GoodSit, we welcome you, sir, to deliver the talk.
Thank you very much and very good morning to everyone. It's really great to be here online, and my congratulations to Dr. Sabu and his team for organizing this event in a renamed university. It's a digital university. That's really, I liked it. So, and that is the need of the time also. So thank you so much. So what I'm going to basically talk about very briefly about some technology that are really required if we want to move towards the industry 4.0. And the companies, they have realized the benefits of moving to the industry 4.0, and they have been basically using these technologies in their enterprise and their organization. So before I start, I'll first play a movie which I have basically taken from the YouTube, and that will basically give you a complete, summary of this revolution from industry 1.0 to industry 4.0, and why do we need to move towards basically industry 4.0. Okay. So I hope you can hear this. So here you go.
When technology changes, the world changes with it. History has been witness to industrial revolutions that have taken place over the ages. The first revolution, triggered by steam power, proved that manpower is not the only way to progress. Machines joined muscle and reduced human effort. The second industrial revolution brought the world together with electric power. Leaps in technology paved the way to a new way of life and a global economy. Then, the computer changed everything. Information technology and electronics led the third industrial revolution. Workplaces became smarter, technology got personal, and communication went mobile. The fourth industrial revolution is bringing together physical and digital worlds across industries to create an interconnected global value chain. Powerful technology, incredible connectivity, and unlimited information is available at your fingertips. Breakthroughs like machine learning, artificial intelligence, augmented reality, blockchain, robotics, and Internet of Things are rapidly changing the way we live our lives. The consumer is at the center of a connected ecosystem that delivers personalized needs at any time of choice. Business leaders across the world are gearing up to be a part of this ecosystem and be omnipresent for their consumers. New players enter and disrupt the game every day while constantly changing the rules. Organizations must change the way they work and strategize while adapting to the new world. It's time to leverage emerging technologies and seek collaborative opportunities to provide new and personalized experiences for everyone. Digitalization brings the world closer by erasing physical boundaries and breaking limits. It's important to keep up with the demands of a transforming world that seeks access to incredible opportunities in the most intimate of environments. Are you ready to lead the fourth industrial revolution?
Okay, so I don't know how many of you heard the voice. If you have not heard, I will send you with the link on the YouTube. Please have a look. And this short video really summarizes that how the industries or the technology has been, deployed in the industry uh, to meet the demands of that time. Okay. My background, as basically you saw in the introduction, I come from a data background, right? So I will start the data journey. And then I will describe basically that some of the technologies that are needed to bring this revolution of Industrial Revolution 4.0. So those who have been working in the data area, in the information management, quote and unquote area, if you see the data management journey, let's say start from the late 60s or early 70s, when the relational databases got evolved and they got invented, and IBM Synology Research Lab at that time used to call the Synology Research Lab. Now it's IBM Almaden Research Lab. Since then till today, this community really feel proud. They have contributed so much, right, in creating the advanced or the intelligent or the trusted information systems. So let me start basically the story from late 90s or the early 90s. People were working on developing the called enterprise data warehouses that basically collects the information from multiple, typically the homogeneous repositories, and summarize, aggregate that information, dump it at one place called the warehouse, data warehouse. And that data was typically being used for mining the data, for generating the reports, right? For doing some kind of discovery of the information, what are the hidden patterns from that data that they are emerging, so that they can use those decisions or those insights to take the right decisions for the enterprises. So these warehouses were designed from the homogeneous data sources. They were pulling the data from the homogeneous sources. In the late 90s, now people started realizing, hey, we have a lot of insights or nuggets, right, in the unstructured data. How we can leverage the enterprise unstructured information along with the enterprise structured data, so that basically we can derive the insights conjointly from structured and unstructured data. And the researchers, particularly from the academia, they started developing the solutions for integrating the structured and unstructured data, whereas the enterprise, they were still focusing on integrating the information from the structured data, but very little unstructured data. So in the late 90s, and many products that came from the database vendors, particularly since I worked for the IBM, let's say IBM Information Integrator, the InfoSphere information integration, that was basically pulling the information from structured data sources, defining a virtual or the mediated schema, so that the users can write a query, and those queries can ultimately decompose and executes on each of the data sources. And if the query requires any unstructured information, that query basically was integrated in the form of predicate called contents in the SQL query there. Now, then people have started realizing, hey, we have lots of other kind of unstructured information, right? it could be basically images, it could be videos, it could be sensor data, it could be streaming data, lots of other information, which again the enterprises are not making use of that data for deriving the insights. Can we basically leverage that information along with the other enterprise and information, operational and the transactional data, right? So then they started dumping the information, because some of the information were coming from the sources which was not trusted, or the data was not that clean. It was containing some noise on that information. So they were getting the data from various channels, dumping the data into the called the data lake, right? Dumping that information there, and then people built a bunch of algorithms on top of it for doing the data curation, different aspects of the data curation, different aspects of the data discovery, different aspects of data linkages and the data integration, different aspects of the entity discoveries, and so on. And therefore basically curating that data, put it in some respectable form so that that data can be analyzed, right, by different methods, right? That's good, right? So all this journey from here was kind of passive in the sense basically that you apply the algorithm does some work, and then you bring that data into the database, and then basically then you apply other set of algorithms for the data analysis, right? Now what is emerging is how we can make this whole process, right from data identification to data ingestions to the data analysis, how we can bring the intelligence in every part of this data ingestion to the data analysis cycle, so that we can understand the data at the source when the data is being ingested, rather than basically understanding the data once it has gone into the database, right? That is what is basically is called the cognitive or intellective or the autonomous information systems. And this is what is the need for the industry 4.0, is that let my data be, how we can make the data active by itself, so that basically data as it comes, basically the systems can understand automatically that data, reason from that, do the reasoning from that data, understand the underlying concepts, the ideas which are hidden in that data. Maybe that data may be related to some other enterprise information, so that you can derive some reasoning, and from there you learn that some kind of knowledge or some kind of insights, and feed that again. That will help basically to understand the further incoming data, right? So this is what is bringing the big data, which is basically the data which is in large, with the high volume, with the veracity, right, with the streaming data, and applying the AI, so that basically we can make the systems more actionable, right? Rather than someone basically go and analyze the information and then take the action, can the system be intelligent so that the systems can become more thinkable and the actionable, right? And that is what basically the need for the industry 4.0, right? And the other is, the previous speaker said, is about how to make the data more trustworthy, right? How to basically make the data secure, right? Although there are n number of algorithms are given over there, but these algorithms, right, they work perfectly, there's no problem. But in the context of the big data, if you want to really make it a distributed or let's say non-centralized system, right, how we can make it, right? So I will touch basically about little bit on each of these technology and more on the data analytics. Okay. So now, to make the system autonomous or intellective or cognitive, as I said, we really need to get the raw data And from raw data, we really need to derive the insights from there, right? So this is the information flow in a intellective and cognitive systems, where we gather the information from multiple data channels or the multiple sources, right? And you have all kinds of data over here, right? You have structured, you have unstructured, you have a streaming data, you have a sensor data, you have audio, video, and all kind of information, right? And this information is coming from a variety source of information. Now we need to basically identify that which data is of useful, which data is of my structured type, which can be basically modeled in one way. So therefore, basically you have a number of modeling, number of ways to model this information. Not one model may suit for all kinds of information, right? And this is what basically is here, that once you bring the data, model that information, then we need to understand that information, that what is this all information about? Does it basically connect to any other piece of information stored in any other data sources, right? So from there, you bring this huge, entity relationship kind of graph, where it makes the contextual information deriving from the data and the relationship between the data entities, right? And then we analyze all that informations to derive the underlying key ideas, the key concepts on there. And that once we have understood that data, we learn from data, provide the feedback so that we can understand more better from the incoming information, and then data gets ready to drive the intelligence. And one of the important aspect of the any cognitive systems for the industry 4.0 is that how my, once you have got the data, there are n number of users that they would like to consume that information. Now each user can understand the beauty of data differently. They can appreciate the data differently. They can consume that information differently. So how we can adapt, how we can adapt the data and the delivery of the data to each of these consumers, so that they can consume the information in a better way, right? And that can be done by learning the user's behavior and the interaction pattern, so that we can improve the context of the delivery, right? So if you look at this data, right, how it is being collected in the real scenarios. So the data is generated from various devices. So you have on the left hand side, you have various devices, right? These devices are basically generating my tons of data. And between this device and to the end data storage, whether it's on the cloud or in your enterprise systems, yeah, right? The number of gateways basically this data goes through, right? So the data is generated, it goes to the gateway on there, and then it gets collected on the edge. So some kind of analytics, we call this a fog analytics or the edge analytics, can be done on the edge itself before basically goes into the cloud or into the backend data storage, right? So we can analyze this data in a very lightweight data on the fly, right? Then it flows through the network and then goes to the storage, to the cloud storage, right? Now the data can be pulled down from the cloud and can be done the analytics. There are different kind of analytics one can do, right? We will see in the next slide. One can do the descriptive analytics or the application analytics, right? The prescriptive analytics, predictive analytics, then the prescriptive analytics, or the cognitive analytics. And as you go in this, in this higher level of analytics, you have to basically bring more intelligence in the system by learning the data, by understanding and reasoning the data, right, in the system, so that the systems can take the action by itself. So now let's see basically that what has been the journey of the data analytics. That is what is the analytics maturity. So analytics, people have been doing this analytics from age, right? A lot of enterprises, they do the analytics only on the Excel sheet, right? They don't need basically any data analytical tools. They do on the Excel sheet. But however, these Excel sheets are also very limited. We cannot do the higher level of analytics. And as you go to the higher level of analytics, right, you are moving towards the systems of engagement. So my pure operational and the transactional databases, right, like Oracle, DB2 and all that, basically they are more transactional systems, which are the system of records, right? So what you do basically, you just pull the data from there, run simple query, basically SQL queries, you run the simple SQL or embedded SQL programs on this data to analyze the information. As you are going from the system of insights, then basically you want to know basically what is going on in my system, right? Then you move to the predictive systems and the prescriptive systems. Predictive systems, we all know basically that can analyze the future trends, can predict basically that what is going to be the demand in the marketplace for so and so things when we analyze that. Prescriptive things is for you are analyzing the information and then you see, hey, 5 years down the road or 5 days down the road, basically you might need that thing. So it's just like a very simple example. When a patient goes to the doctor, doctor basically gives the prescription that the patient has only the the cold, right? But then doctor basically sees that after 2 days it can become a feverish kind of things, and therefore basically the doctor prescribes some medicine to prevent those things, right? So those are the prescriptive analytics, that to see basically that what is going to be in the future and to prevent that things not to happen, or if to happen then what to do for that. And the last is the cognitive analytics, which is more on the interactive analytics, right? You ask the system that, like a chatbot is just one example of the cognitive analytics, right? Of the cognitive interaction. But if we given the chat box, if we can analyze in a free format one and can have a deep NLP queries on that, that is what becomes the cognitive analytics. And the technology that you require for each of them, right? Many of you have already done. As I said, for the descriptive, you can do simple on the Excel sheet or the SQLs, right? And those kind of things, right? For the predictive, you need some little bit more, advanced tools like some kind of data mining tools and so on, right? And these are the technologies basically that are used to write the algorithms for developing the predictive or prescriptive or cognitive algorithms, right? Now the last part I'll just say very briefly is about the blockchain. So I'll just show you 2 or 3 slides and then I'll stop here. So blockchain, to me, it is a very big hype. And if you look at the trends, I've taken this graph, I think a couple of months back, right? If you look at, go to the Google Trends and type AI, ML and blockchain, you will see basically how people are searching the information on the Google, what is the trend of these buzzwords of AI, ML and blockchain on the Google. And you see basically that, look, this ML is consistently going, right? AI is similar way also, right? But the blockchain, which is the blue one, there was a really big bump in some time, is basically, late 17 or early 18, right? Where a lot of people were wanted to know about the blockchain, right? So can we conclude that it is a hype, right? To me, probably it is more hype than the actual things, right? Because there are very, very few real blockchain applications, right? where you can leverage the blockchain in the true sense, right? So the first question is how we can find it out where we need a blockchain. I give lots of talk on blockchain. People say, can we do this application, that application, or this application? And 99 or 100% of the times, they all can be done using my centralized databases, or maybe in the distributed databases. So the question here is, if we have some requirements in our mind, and we need to choose the technology, should we use the relational, some centralized database, or distributed databases, or the blockchain technology? And here is the very simple thing here, right? So what this says is that when you are executing, when you have a single transaction, and that single transaction requires the participation of multiple parties, and each party is doing some updates in the database, right, for their part of the transaction, and there is a lack of trust between these parties, right? If the answer of all of them is yes, then you may think of the use of blockchain, else it is a killer part. It is, you are basically, overkilling your application with the blockchain technology. So again, when a single transaction, one transaction, so for example, I'll take, let's say, in the logistics, so we are sending exporting the things from India to another country. That basically item goes from multiple parties. There is a custom one, there is a shipping one, and then similarly from the destination side, that multiple parties are involved. But the transaction is same, which is that we are exporting the item from place A to place B. In this transactions, to fulfill these transactions, to have a successful delivery of items from A to B, you have multiple parties involved in that transactions, and each of them are writing on the database for their part, right? And these parties are independent to each other, they don't know, therefore there is a lack of trust between these parties, and therefore this is the example where we should leverage the blockchain. Not the basically one that many of our colleagues or friends, right, they have been thinking about, hey, we can use the blockchain, we can replace the other systems by the blockchain and so on. As I said, they are all the overkilling, right? So with that, I'll stop here, right? And these are the technology that are really very much needed for this industry 4.0 revolution, and these are some of the only technologies you saw basically many of other things in the video. You need the AR, right, VR, robots, and other ones. So with that, I will stop here. We still have couple of minutes. If you have any questions, I shall be very happy to answer.
Thank you, sir. Thank you for taking us through a quick journey through the data analytics now and then, and discussing some of the recent trends in blockchain. If audience have any questions, you can post it on Q&A. There is a question from YouTube. May I read it?
Sorry?
Sir, there is a question from YouTube
Okay.
chat. May I read it?
Yes, sure.
Is it relevant to put software updates, issues, and attacks in blockchain?
Sorry, say it again. It is relevant to update software.
Is it relevant to put software updates, issues, and attacks in blockchain?
Sorry, I could not understand the semantics of that software update. Probably I can take the offline this question.
Okay, sir. Any other questions from the audience side? Sir, there is one question. UAE is going paperless with the help of blockchain. Your view, please.
Okay, okay. So UAE is going paperless with the help of the blockchain. You're right. So some of the applications in the UAE government, right? Yes, there is a need for the blockchain. As I said, the simple algorithm is for one single transactions, multiple parties. If in the UAE, for example, if I need to set up an industry in the UAE, in Dubai, right? Now to set up that industry, I need to take the permissions from multiple government departments, right? I need to basically take from the environmental clearance, I need to take from the commerce clearance and so on and so forth, right? And probably the decision of the second party may depend on the decision on the previous party. Is it a good example? The answer is yes. But can you do this by other way? The answer is also yes. You can do it on the workflow, right? The other example could be basically, let's say from an Indian perspective, the Indian government from the federal central government releases the 1 rupee, and our late Prime Minister was saying that in actual field, it only 15 paisa reaches, 85 paisa goes basically in the pocket of the different mediators. Now, when the central government is releasing the 1 rupee, it is releasing for some work. And for doing that work, there could be a multiple parties involved. It goes to the state government send it to the district one, district basically finds the different vendors finds the different suppliers finds basically different, thekedars and so on, right? And the finally money goes over there. If they write the record in the blockchain at every step, so that it brings the transparency and everyone can see, yes, a 1 rupee job which was sent from the central government has reached to the direct person who has completed that work, right? Yes, that is the example of that one, right? So can it go the paperless? Does not mean it's a blockchain, first of all, right? Paperless means you and I are sending the email, it is a paperless, there is no blockchain there, right? So saying the paperless with the help of blockchain, I think it is a overestimating this thing. Can we do the paperless? The answer is yes. Something can be done with the blockchain, something can be done by otherwise also.
Thank you, sir. Is there any more questions? I think there is no more questions from the audience side.
Okay,
Thank
great.
you, sir.
Thank you so much.
Thank you, sir, for joining with us.
Yeah.
Have a good day.
Bye. You too.
Our next session is handled by Dr. Srinivas Padmanabhuni on the topic Industrial AI. Dr. Srinivas Padmanabhuni is a PhD in Artificial Intelligence from University of Alberta, Edmonton, Canada, and has been awarded the title of Eminent Engineer by the prestigious and renowned Institution of Engineers. Srinivas co-founded CityMandi.com, a next-generation AI-enabled smart B2B startup in agri-tech focused on farm-to-fork. He has been the past president of ACM India and is the chief mentor of Tara Technologies, an AI consulting and training company. Earlier, he was a principal research scientist and associate vice president at Infosys. He has won several other awards, including the Excellence Award for Innovation at Infosys, Research Excellence Award at University of Alberta, and Merit Award at IIT Kanpur. His interests include AI, machine learning, software engineering, and cyber security. He has, to his credit, 7 granted patents, multiple additional patents in process, one published book by Wiley, 100 plus referred international publications, 400 plus invited talks across 8 countries, more than 15,000 students lectured on AI and related topics, and more than 4 startups. On behalf of Kudsit, we welcome you, sir, to deliver the talk.
Thank you. Am I audible?
It's audible.
Yes. Thank you. Thanks to the Digital University Kerala for this opportunity, and wishing the university all the best in these modern circumstances. I think it's a very welcome move. So my endeavor in the coming half an hour will be to I'll primarily look at industrial AI from two perspectives. One is there is some notion of what we call as AI coming to our daily life. But what people don't understand is there's a lot of application of AI in conventional industry also. That's the angle I'm trying to bring in. Then in doing that, I will talk about two particular aspects. One is what are the industries where AI is getting to transform the overall process and bring order of magnitude of productivity. And then I'm going to talk about some of the emerging use cases and industrial consortia which are working towards adoption of industrialization of AI in several verticals. And the second part I'm going to talk about little bit is if you want to industrialize AI in practical terms, we have to be really careful about the acceptability of AI as a mainstream technology while complying with compliance needs, while taking care of safety. And that is one area where AI has been unfortunately not so successful. So let me put some shocker into this aspect and give you some view of what is meant by showstoppers to industrial adoption of AI and what is needed to overcome that. It is in that direction that I have been doing a lot of research, and we'll come back to some recommendations and some of the work which we have been doing. So before we go ahead, at a broad level, when we talk about AI, a lot of people talk about several things. It talks about replacing humans with machines. But ultimately, what we feel is it is a sense and respond technology. Humans have this too. We see something, we respond in response to what we see. We hear something, we act in response to what we hear, etc. So in general, the purpose of building artificial intelligence systems is to look at how we can create systems which can sense, and in that sense of the word, they replicate human senses. For example, if you see computers today are able to see just like humans with the use of AI technology called computer vision. Computers are able to write and read like humans with the use of language as a technology called NLP, which is a part of AI. Then computers can speak and understand speech like humans with the help of technologies like speech understanding. But all of it ultimately is about, okay, all of these senses give data to the AI system. But what is the role of AI? The role of AI is to respond in a appropriate manner to what it has sensed. For example, if you are running a automated AI-based health diagnostic program, it should sense, means by emulating the sense of seeing the X-ray, and what it should respond saying that the pattern looks like, okay, there is cancer here. Or in case of a more complicated AI system, like say driverless car, it will look around, look at the speed of the car's neighborhood, look at the traffic lights, look at the lanes, and it will respond with appropriately braking and putting the accelerator at a certain level of speed with the steering in the right direction so that it conforms to traffic, does not hit anybody, and goes ahead forward like a human driver would do. So in general, I would say this one slide reflects a view of AI as emulating human senses. And once the senses send data, there is a need for response from the AI system. When the response is to be given, it tries to extract patterns from the data, which helps it in deciding what kind of response to give. So at a highest level, you can think of as AI emulating the human capability of sensing and responding. Okay. Now, if we talk about all the world of AI, lots of work has been going on in applying AI to very practical systems like playing very specific games, applying it to solving problems of healthcare in diagnosing cancer, even to the level of emulating driverless cars. But today, still, if you look at the original definition of AI, where if you are to emulate a human level intelligence, we're still falling short of it, because the way today's AI systems are built, they're built on the premise of what is known as you get tons and tons of data corresponding to a specific domain, train the system on that, and you get an intelligent system, which is what we call as probably a narrow intelligent system. Like you can have world chess champion in Deep Blue, or world Go champion in AlphaGo program, or world Jeopardy champion in Watson program. But the moment you take a Watson program, which is programmed for, let us say, Jeopardy of natural general knowledge questions, you go and ask it to go and apply it in healthcare scenario, it will fail drastically. Same way a AlphaGo trained on, let's say, Go, ask it to go and play chess, it will fail. So these are very narrow. When you say narrow, it is important to understand that they are very, 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 very narrow updates which are going on in terms of the particular domain and what it can achieve for that domain. The moment you change the domain, they're not anymore working with the same efficiency. Whereas humans, if you see, if you learn driving in India and go and drive in US, it does not take you more than a couple of hours to acclimatize to the driving and you can continue driving. That's the power of versatility of humans. And that dynamic reconfigurability of systems is absent in today's AI systems, which probably will be realized sometime soon with the realization of general level human level AI, which is called as AGI, or artificial general intelligence. But that will be some decades away. Once you have that, probably you can even be better than AI systems of AGI, where it can beat humans in every facet. We call it artificial superintelligence. But today, ANI is the talk of the day, also known as weak AI, where you train that system on a large domain with lots of data. Data could be coming from history, or could be coming from sensors, could be coming from past transactions. But they guide the system to behave intelligently based on pattern extraction from the current data that is fed to the ANI system. Now, in terms of application of AI, there are two broad schools of thought from an industry usage of AI. One, what we call as consumer AI. This is something which affects every one of us, every walk of life. It could be customer service, it could be search, like Google search, applying it to everyone, e-commerce, where everyone tries to apply, marketing. Name a scenario where you can use any service which is affecting end consumer. AI is coming there. For example, today, personalization of services, personalization of education, personalization of offers is something which we are very, very commonly used to because of application of AI. So when it comes to having end consumer in mind and developing an AI application, I would call it consumer AI. But at the same time, I make the domain a very industry focused, where it is B2B. Consumer AI is B2C, where application of technology is for business to consumer, whereas industrial applications are about business to business, or businesses or industries which can adopt AI. So we see AI applications in several industries. Could be supply chain, could be automotive, could be manufacturing, could be transportation. So let me delve deeper into two aspects of industrial AI. One is what we feel is the notion of what are the industry processes which take advantage of AI, which is what we talk about industrial AI. Then what I'll talk about is from an industrialization of AI, means to make AI more mainstream, to make it more mature, what are the gaps and how do we address them? So let's look at a very important industry. I think our previous speaker, Professor Mukesh, talked about, right, where blockchain was required in some areas. One of the areas where it's probably useful is the logistics and transportation. Same thing about industrial AI. And one more thing which I said, tying to my earlier definition of AI, sense and respond. So it is possible that AI by itself is not the complete cycle. It's about working along with smart sensors. So if you talk about smart sensors via IoT, via beacons, via different technologies being deployed at different locations and making use of the data obtained by sensors by applying AI algorithms on top, you get lots of useful applications in logistics and transportation. I think the biggest one which I would look at is what I call as supply chain visibility. If you look at supply chain visibility, it's about dynamic, adaptive, real-time visibility of where your goods are. Is there a bottleneck somewhere in your supply chain? Is there some process which is hindering the progress? Is there some parts of the supply chain which is moving slow? Is there some place where there's a breakdown in the traffic which is causing the issue? All that can be obtained by combining sensors with AI. Then in terms of tracking, let's say tracking ships, tracking buses, tracking trucks, etc. It becomes a useful trick. Then intelligent warehouse monitoring. Today, not just about warehouse monitoring, but also warehouse management is now being outsourced to robots, which are highly vision-driven, automated, which can pick up things, locate, place them, deliver from one place to another. And in fact, in the last years, I think last year or last years, what we call as a $1 billion day equivalent for Alibaba. In one day, they had $23 billion of sales. And that could not be possible to be managed without extreme AI plus IoT enabled warehouse management in their backyard. We saw some of the robots which are working with highly powered vision technologies to enable pick up things, delivering, coordinating with one another, delivering from one place to another in a very automated manner. Same way, if you look at location-based services, today there is ample vertical startups which are talking about applying intelligence based on location. Example is companies like Uber, Ola. They're great examples of how they use location-based services, and they use a lot of AI in between to optimize routes, to optimize find people who are at different locations, to optimize allocation of drivers, etc. So in terms of logistics and transportation, there is a very big use case of industrial AI. And last but not the least, by virtue of streamlining of process, it's possible that you can have a paperless or you can have any stopless straight through processing from one source to one destination. Likewise, you can have smart traffic. We already are seeing lots of autonomous modern cities. We call them smart cities, which have smart traffic applications using applications of vision plus sensors. In case of manufacturing and discrete manufacturing, high-tech manufacturing, all of the kinds of manufacturing, you already heard of Industry 4.0 as a trend, right? Today, Industry 4.0 is all about AI, IoT, IIoT, industrial IoT, for cyber physical systems, making a possibility of deploying sensors in every machine, every asset, and harnessing the data thereof using AI to make really smart process. What could be a smart process? Some of the smart process are asset lifecycle management, understanding assets, visibility of assets, where they're moving, where tracking of assets. Process optimization. If you look at currently, there is a way of doing the process, and by looking at analytics of the data, you can see if you can optimize the overall end-to-end process. Straight through operations is something I mentioned example, right? Where you had workflows with manual handoffs at some places. Can we, by just doing data-driven approach, do end-to-end automation with straight through? And supply chain visibility, we already talked about. Field service automation. This is something which is today a fairly common, at least in areas where we are seeing personnel carrying AI-based applications to diagnose, to carry out applications which are around field service without necessarily going through manual workflows. And last but not the least, and most important, is I would say the massive jump in the MRO, which is maintenance, repair, overhaul industry, which is a significant part of many industries and a significant budget consuming component, moving from the regime of reactive maintenance to preventive maintenance. So when I say preventive maintenance, I actually am talking about a focus here is to move from conventional reactive approach to repairing something when something bad happens to something where you can use IoT, AI, and Industry 4.0 technologies can be used to understand potential scenario of maintenance, potential overhaul scenario, potential breakdown scenario, and flag it before some repair needs to be done. And that can be a huge savings in the industrial maintenance scenario. And so what we feel is moving the regime from reactive to preventive maintenance is one of the biggest benefit we can see in the area of industrial AI, where looking at data from previous maintenance, looking at different data from machine failures, machine sensing capabilities. So these can be new machines or it can be retrofitted. If you have legacy machines, you can fit sensors, retrofit, and get to a regime of preventive maintenance. And believe me, preventive maintenance is something lots of industries are getting to really put in a priority because of emergence of Industry 4.0 with IoT and AI at the core. So in terms of additional areas where we're seeing lots and lots of applications in industrial AI, in manufacturing, high tech, as well as a lot of the large industries, is areas like asset monitoring, diagnosis of machinery, as I said, predictive maintenance, followed by preventive maintenance is an overall regime. Monitoring of environment, for example, if you want to see if there are certain categories of PM 2.5 and certain environment variables which need to be constantly monitored and alerted, we are talking about monitoring with sensors and delivering alerts via AI. Pollution monitoring as part of that. Quality control. This is again a very interesting area where we're seeing lots of interesting ways of inspecting finished goods by use of computer vision and flagging off any defects without necessarily a human being there at the center and doing a manual verification. Supply chain traceability and visibility we already talked about. Then let us talk about something which is very potentially very, very revolutionary from the maintenance perspective, auto tuning of machinery. Today, we're talking about some of the machines which are using the concept of AI-driven diagnosis and repair so that they can not only diagnose about having an error, but they can also correct themselves if they have to be tuned. And that's a hugely, very, very, very welcome scenario for maintenance perspective. I'll come to the telematics and connected car in a later slide, but that is another in a whole new vertical where the driverless car and its surrounding ecosystem is yielding a huge manufacturing base and surrounding parts surrounding ecosystem of providers, etc. So overall, if you see, there is a massive improvement in process and technologies which can be done using application of AI and industry 4.0 based on IoT plus AI. So as I said, in 2014, industrial IoT was supposed to reach 500 billion. I think it is more or less reached there, and going forward, probably it will be even further. So as we said, we are talking about predictive analytics, predictive maintenance, offering the facility of capturing real-time data with proactive warning leading to preventive maintenance as the main source of improvement in maintenance. Now, all of this is fine, but is it getting into practice? That's where we see that there is a worldwide effort at operationalizing industrial AI by using IoT plus AI. This consortium is called Industrial Internet Consortium. They've come up with a federation of a lot of industries who are chartered to enhance adoption of IoT plus AI kind of ecosystem. They have come up with several different architectures for several industrial processes, which are very much important for all these industries. Several test beds they have created, like for asset efficiency, for track and trace of assets, for factory operations visibility, intelligence, and mostly condition monitoring and predictive and preventive maintenance of assets. There are several such test beds which are being used. And as a result of this, what we're seeing is AI plus IoT is getting into mainstream industry. So I was talking to you about connected car and the driverless car ecosystem. Today, there is a whole ecosystem being developed around the whole autonomous car, which is ultimate AI application. You have autonomous solutions at the top level, whereas internally there are sensors, there are development tools, connectivity tools, mapping tools, algorithms tools, security tools, and different integrators. So what we need to look at is very, very, very important dimensions of autonomy leading to a new level of industrialization of AI, leading to a new industry. So if you see this is actually a part of the overall data generated from such kind of autonomous cars. And you see what you can have in the future when you have huge number of revenue possibilities where car generates data and you can use a huge number of monetization opportunities around this kind of data. You could have shared mobility services, car data related services, etc. So that kind of brings to the second part of my talk, which I'll go very briefly and introduce our solution. What is the roadblock to industrialization of AI? When I say AI is there in all industries, good. But what we also see is from a recent report, we found that more than 50% of deployed solutions of AI had to be withdrawn from production due to several compliance or trustworthiness issues or lack of complete testing. And that's where we find that large AI deployments today are really facing huge issues in the real world. We have seen examples where there have been some technologies which have been withdrawn because of displaying biasness, because of leading to loss of life, because of loss of fairness, because of mistrust. All of this, I feel, is because we have a non-rigorous AI testing environment where developers do testing and developers feel randomized testing where train test combination is good enough for an AI to be successful in the field. What they don't understand is a tester is a tester. If you can understand, if you go to real-time systems in government organizations, how much testing is important. Right from hardware to the lowest piece of software, they do testing 10 times of different kinds of testing they do. Whereas in AI systems, somehow testing is given an afterthought. And that led to our thought process. And today I am pleased to announce that I have just incubated a new startup called testaing.com, which is working towards a product for testing end-to-end of AI products called AI Ensured. So our goal is to ensure successful deployment of AI with end-to-end testing. So we're talking about testing for explainability, testing for adversarial robustness, testing for performance, testing for concept drift, and lastly, but not the least, privacy, which is very important nowadays. And on top of that, we work on end-to-end life cycle of testing, including test data generation and test data process management using experiment management solutions, etc. So for lack of tools in the market, this prompted us to start this tool, because wherever you see literature in AI, it's all about training, testing, and developers, but very few people are talking about end-to-end testing. And that's where we are coming up with one of the world's first of a kind AI testing solution. We already launched 2 years back AI testing certification, and I'm pleased to say that more than 500 people were certified on AI testing. And it's a great success, because we see testers are now getting excited about getting their hands on AI products. And I think more testers get into AI, the better it's for the AI's future. So with that, I will stop here. This is my contact. If anybody has interest, feel free to come to me, talk to me, and I will be more than glad to give you any more data about what I'm thinking about testing AI systems, what are the future of AI in terms of testing, what are the areas where we need to make it addressable or amenable to compliance and answerable to customers. So game is changing. Winners embrace new mindsets and tool sets, and that's where we are discovering these new tool sets. And our goal is to enhance adoption of AI for the whole world and make it safer and trustworthy. So our goal is to make it trustworthy. Okay.
Thank you, sir. Thank you for discussing on the recent trends and applications of industrial AI and summarizing the problems and solutions regarding deploying industrial AI. Thank you, sir. We have a question from the audience side. What are the precautions taken by companies for using AI in
what
a
are the
secured
precautions
way?
taken by companies for AI in a secured way? Okay. So let me tell you, the answer is, if they were taking it, we would have no need for my product. There are companies who are working on bringing security testing for adversarial robustness. Just recently, we started looking at companies who are paying attention to this. But otherwise, in the rush for deploying AI in the mainstream, they lose out on one big aspect, which is secure deployment. And secure deployment is important because today hackers are looking at new threat vectors in the AI domain. New threat vectors. And these are something which can be as dangerous as if I have a face which I'm using to suppose enter my factory premises. There is a hacker who can just with a mask on top of his face with just 1 or 2 pixel changes can get entry to that or can deny entry to that. Dangerous scenarios. Secure images are suddenly turned insecure by very, very difficult to recognize attack vectors.
There is one more question. Your view on bias in AI.
My view on bias in AI, I think the basic fallback answer of AI systems developers is whatever is there in the data, I just reflect. That is not acceptable. You can have your data 80%, 20%, 80% male, 20% female, but that does not mean that the data and the pattern which is there in the data has to be exposed as is to the system. The system has to be fair, unbiased with respect to sensitive attributes like gender, age, with respect to race, etc., and also with respect to PII, personal identifiable information. There is no justification for using my PII without my permission. There is no justification of saying that data is biased, so I will create bias. So you have to work around the bias in your system. You have to perturb the model to be stratified with respect to the reality of the expectation of being gender neutral, being age neutral, being race neutral, being orientation neutral. And I think it is in the DNA which has to go into the AI systems developers now, because enough is enough. We have let developers run the AI world, but the sad part is even the largest systems which have been deployed now, including GPT-3, trained on real data, where the recluse is we are just reflecting what is there in the real world. and let that reflect into my output of GPT-3 or something is not acceptable. It's not acceptable simply because the real world may be biased, but from going forward, you cannot let a bias which is there in data creep into the output AI and take that as an excuse. So we have to be aware of the extra mile you have to go in fine tuning your data before training your system. And that is something 95% of the systems developers in AI world are not yet paying attention to. I hope that changes in the coming 5 years. It's important because otherwise we are going to live in a world where there'll be more and more biases, more and more, for lack of better word, discrimination in the AI systems, which is a reflection of what is there in the data also. And that is what we want to fight with our tool. We want to create an AI which is privacy aware, which is bias aware, which is segmentation aware, which is compliance aware, and tested for all of this.
Thank you, sir. Are there any more questions from the audience side? One more question. GPT-3, as you mentioned, Google come up with trillion parameters model. Where will this end up? How big it's gonna be?
Yeah, it's going to be successful. I'm sure a lot of people take a lot of advantage in using automated, automated intelligence from a lot of data. But ultimately, let me tell you, it is still not a substitute for human. It will still fail Turing test, my view. It's my view, but just because you have added more parameters. So I'll give you one more anecdote simply. Google said neural machine translation is better than conventional human expert driven machine translation. Good, but I can still find areas where it's still not fully covered in terms of the potential translations, and so it may fail for those scenarios. So all I can say is, okay, more and more data. I think tomorrow GPT-4 will come with 10 times more data, but all I can say is the automation possibilities are huge, but only thing is be aware of the creep of data bias and privacy, etc., which are probably not fully considered when they are training these systems. So that's why it is a huge hammer, but you have to use it with care.
Yes, sir. I think the questions are over. One more question. What are the advantages and disadvantages of AI in recent trends of IoT?
So all I can say is without AI, IoT is meaningless because IoT continue to generate reams and reams and streams of data. But without actual pattern extraction from that, for example, when Progressive Insurance deploys a sensor in the car where it reflects the driving pattern of the driver, but unless that translates into some pattern which the insurance company can dynamically generate billing for insurance premium for that part of a trip which has gone, it's not of much use. So similarly, when a machine is fitted with a sensor, the data is sending it, but as long as the wear and tear data is not used for proactively flagging a warning for potential failure or something, it cannot be used. So all I can say is, except for small toy applications where you're happy at seeing some visibility of current pollution level, but that's it what IIT can do. But beyond that, from the complex events and from the reams of data generated by IoT, it has to be put into proper pattern extraction with AI and thereupon respective action. So without AI, however much IoT you do, it will be futile.
One more question is there. AI in healthcare, Indian perspective versus autonomous automobile or car?
Indian perspective, I will tell you, Indian autonomous driving car is, I don't know, even guess 2100, 2200 when it will come. I don't know, because Indian traffic with managing the cows on the road, the rickshaws on the road, the cars on the road, cycles on the road, and especially the chaos. I don't think any computer vision, I can challenge if any computer scientist of today or tomorrow to handle Indian traffic, to develop a smart computer vision system which can handle the chaos of Indian traffic. Let me tell you that. Healthcare, yes. Today we have lots of examples of coming startups as well as interesting solutions coming up. I don't know whether if you've heard of companies like Niramai Health Analytics. Niramai is by Geeta Manjunath, a good friend of mine, Dr. Geeta Manjunath. They have developed thermal sensing based breast cancer detection. They are applying to, as an NGO, applying to a lot of clinics in rural and urban areas. Very early warning system, very non-invasive, using vision. Then we have SigTuple, interesting startup. They have a diagnostic hardware come detection device using AI. Then recently, lots of healthcare companies like Manipal Healthcare, etc., have been starting to look at AI for specific kinds of cancer. There is a lot of work happening at AIMS, for example. I know some specific doctors who have taken specialization in using AI for specific kind of diseases. Not only that, people are now looking at very, very specific diagnostics. Like, for example, in Tripartite Hyderabad, there was a study of COVID. Let me guess, it's not about using images, but using signatures of the coughs, audio of the coughs. They're trying to use that as a diagnostic for COVID. So a lot of interesting works going on. In COVID times, I'm sure a lot of help has happened, and it is only going to accelerate the adoption of AI in healthcare. But driverless car, please, no, India is not the place. Within campuses, a lot of people are using them for small deliveries, small golf carts going here and there, but outside public roads, no.
Okay, sir. There is another question. What is the evolution of fuzzy logic in industrial AI?
See, fuzzy logic, as said, it has peaked and now it is somewhere gone into one of the many several areas where you do soft computing. So soft computing, you can say, is one branch of AI which has kind of matured, but today with more and more machine learning driven systems, these have become slightly outdated because people now want to develop only data driven diagnostics. Fuzzy logic is where you wanted to bring fuzziness or uncertainty into the systems management. So you had developed some control systems using fuzzy logic, etc. But I think it is getting limited as we go along. As we go along in industry, there's more and more, I would say, the predictive analytics related stuff rather than more of fuzzy or soft computing kind of systems today.
Okay, thank you, sir. Thank you for the valuable session. It was a very good interactive session.
Thank you. Wish you all the best for the university and the program.
Thank you, sir.
Thank you.
The next session will be handled by Dr. Vineet N. Balasubramanian on the topic AI in Industry 4.0 and Digital Transformation. Dr. Vineet N. Balasubramanian is an associate professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Hyderabad. And currently, he also serves as the head of the Department of AI at IIT Hyderabad. His research interests include deep learning, machine learning, and computer vision. His research has resulted in over 100 peer-reviewed publications at various international venues. His PhD dissertation at Arizona State University on the conformal predictions framework was nominated for the outstanding PhD dissertation at the Department of Computer Science. He is an active reviewer and contributor at many, with recent awards as Outstanding Reviewer at CVPR 2019 and ECCV 2020. He is also a recipient of the Teaching Excellence Award at IIT Hyderabad in 2017. His research is funded by various organizations including DST, MIT, DRDO, Microsoft Research, Adobe, Intel, and Honeywell. He currently serves as the Secretary of the AAAI India chapter. On behalf of KUDSIT, I invite Dr. Vineet N. Balasubramanian to deliver his talk.
Thank you very much for the invitation and the kind introduction. Just to confirm, am I audible?
Sir, it's audible.
Okay, wonderful. And can you see my screen? Can you see my slides?
Sir, the slides are visible.
Wonderful. Thank you. Thank you. All right. Yeah, thank you again for the invitation and the very kind introduction. So I think the talk that I'm going to give now is a nice segue from the previous talk by Srinivas Padmanabhani. Some of the topics that I'm going to cover will be a nice follow on from what was discussed. So the topic that I'm going to talk about is one important facet of AI in an Industry 4.0 and digital transformation, which is explainable AI. So I primarily work in the areas of machine learning, deep learning, and computer vision. And explainable AI is something that we work on. And I hope to talk about some of the works that we have done too in the later part of the talk. I'll try to keep my talk to about 25 minutes, so there'll be some time to discuss towards the end on any questions or any other thoughts. So I think I'm quite sure all of you are probably more aware than me on what Industry 4.0 means. So if we had to look at the landscape of industrial development, industrial revolution over the past few centuries, it started with Industry 1.0 in the 18th century, and we talked about the steam engine, mechanical production, and so on and so forth. Then came the 19th century, Industry 2.0, when electricity became the main focus of the revolution, and that also led to a lot of changes in the manufacturing pipelines, mass productions, assembly lines, so on and so forth. Then, of course, came towards the mid of the 20th century, probably later part of the 20th century, which was Industry 3.0, which was all about electronics, ICT, and to a certain extent, internet itself. And today what we're talking about is Industry 4.0 and how it's digitally transforming the entire landscape of the industry. And I think if one had to put keywords around the technologies in the Industry 4.0 framework, you have IoT, location detection, cloud computing, augmented reality, 3D printing, AI and big data analytics, of course, advanced robotics, smart sensors, all of them. You've heard quite a few so far in the different talks, right? And obviously, all of you know by now that AI is everywhere in the Industry 4.0, right? So in any of these, be it augmented reality, be it robotics, be it Internet of Things, AI is an important component of all of these aspects and technologies of Industry 4.0 and digital transformation. So then the question then is, why do we need explainable AI in this context? Why cannot we just use machine learning as it is? I think the previous speaker very nicely motivated the need for trustworthy AI, and I'm probably going to expand on it, focus on it, and talk about what people are doing about it today over the rest of my talk. So if you look at the popular GDPR, which is European Union's General Data Protection Regulation Act, in somewhere around the mid 2019, European Union modified its GDPR Act and added this clause that says a business using personal data for automated processing must be able to explain how the system makes decisions. Okay, this is now a law in the European Union. How does it affect us? If you take any company that's manufacturing a technology for European Union, I'm going to take a software example, but I think you could consider this for any other kind of a technology too. Let's say there was an Infosys or a CTS or a TCS that was developing a banking solution for, say, a bank in Germany. And let's assume now that AI or machine learning was being used to make a decision as to whether a customer's loan should be approved or not. Now, what this law says is if a customer's loan is declined, now the customer can go back to the bank and say, tell me why you made this decision for my application. Now, if the bank used a software, unfortunately, if it used a black box machine learning algorithm, say neural networks, the bank has no clue why the decision was made. Right? So maybe the bank will go back into the candidate's files and look at it, but it does not know how to explain why the machine learning model made that decision for the customer. Which means these kinds of technologies cannot even operate today without an explanation for the machine learning model. So explainable AI becomes a very important component of these solutions. This need not be just for a software technology. It could be for any other technology too. Right? This is just European Union, but similar laws exist everywhere too. In fact, there's an entire Wikipedia entry, and obviously this talks about laws, which talks about the right to explanation. Right? So there's a fundamental right to explanation. It wasn't talked about in the context of AI before. In fact, one of the earliest contexts in which the right to explanation came was in explaining how people got different credit scores. Right. So today we talk about in India we have the CRISIL, which gives credit scores to different individuals, credit based on their credit worthiness. So an individual has the right to go back and ask the organization, why did this credit score get assigned for me? That's the right to explanation. That was the context in which it was initially developed. But today the right to explanation is more broad, and wherever AI is being used, it becomes important to have a right to explain for a customer, for a citizen, to have a right to explain how a prediction was actually made in any kind of a setting. Now, why is this right to explanation important in Industry 4.0? Right? So let's take a few examples. I think a lot of these examples, interestingly, was talked about also with the previous speaker. Let's take a few examples of where Industry 4.0 focuses on, be it healthcare, be it manufacturing, be it insurance, or be it autonomous vehicles, all examples that were just talked about, right? So in each of these cases, if AI is being used for healthcare, a very important question to ask is, if a patient, let's assume we have a machine learning model that looks at chest x-rays and gives a certain risk level for COVID positiveness for a patient. Right? So just because a model gives a certain probability, will the patient walk away from a hospital even if he or she has a symptoms? Wouldn't we want to know why a model makes a certain kind of a decision? It's extremely important in these kinds of scenarios, especially in healthcare. Similarly, let's talk about manufacturing. Right? Again, the previous speaker spoke about predictive maintenance, prescriptive maintenance, very, very important parts of the next generation manufacturing industries. Right? So an important part of these of the use of AI for manufacturing is to look at where machines could be faulty, could have anomalies, and a counter question there is to say, why is a particular part of the manufacturing pipeline faulty? What should I repair? One aspect is to inspect, let's say, for example, a set of solar panels in a solar farm and say that some solar panels are faulty. Right? It helps because then the company can dispatch some engineers to go repair them. But the next part of it is to say, why are you saying it's faulty and which part of it was really faulty? So it becomes important to find this out. And this becomes even more complicated in very complex manufactured systems such as aircrafts. There are thousands of sensors. How do you find out which one of them led to a certain outcome in a particular scenario? I mean, apparently in the aerospace industry, whenever, say, a flight has a bad landing, 75% of the times, even if pilot files a report, the support engineers have no clue how that particular event happened during the course of the flight, because there are just so many sensors there and it's difficult to find out why something happened. So as AI becomes used, it becomes even more important to answer this question in the context of using this in the industry. Similarly, in the insurance industry, a question could be, there could be a regulator. If a machine learning model was used to profile a certain customer, an insurance regulator may want to access and understand why a particular decision was made. And finally, if there was a self-driving vehicle and that took a certain path, why did that vehicle take this predicted path? Again, as the previous speaker said, maybe self-driving cars and autonomous vehicles are a distant dream in India, but autonomy in the autonomous vehicle industry is talked about in 5 levels, level 0 to level 5. Level 5 autonomy is a pure self-driving cars, right? But we could still in India talk about level 1 autonomy, level 2 autonomy, simple things like a driver is sitting in a car, but if there is an obstacle, maybe the brakes should be pressed by a sensor rather than wait for the driver to pay attention to an obstacle on the road. Those kinds of tiny levels of autonomy perhaps can come into the industry in India. But even there, an important question is, why did the AI system being used make a certain decision? Very important conversations to have. right? Let's take one step back and ask ourselves, where is machine learning successful today? So if you looked at all the successful machine learning applications of today, some of the questions that they try to answer is, what is the product relevant to the user, right? Take Amazon, Flipkart. What is the sentiment of this tweet, or what is the sentiment of this review, or what are the objects in this image? These are the kind of questions existing AI machine learning methods try to answer. And if you had to abstract the question out, the question is, what is X, right? Whatever that X be in a given application. And if you observe carefully, wherever you use machine learning daily, take your phone, take your Facebook face detection, take your Google Translate, take your Amazon product recommendation systems. In all of these scenarios, the cost of a bad decision is low. You get a bad movie recommendation, you lose 500 rupees, you lose 3 hours, you don't lose your life. And often in these kinds of scenarios, accuracy is all important, right? So for every model that comes out, a certain model gets 93% accuracy, then the community around the world now fights for crossing that barrier of 93 and going to 94 or 95, right? Is accuracy the only metric that we want to look at? Isn't it too one-dimensional? Are questions to ask. Then what do we really want, right? What are we really looking for? If that's what machine learning is about today, where we really want to go is the use of AI in complex real-world systems, which is what Industry 4.0 is all about, where there is high risk and the system could be safety critical, be it cockpit decision support, where a single mistake could lead to loss of hundreds of lives, or medical diagnosis, once again, loss of life. And in these kinds of applications, the cost of a bad decision can be very high. It's life or death. Right? So it's okay to use AI ML when you know you're going to lose 500 rupees. But the moment you're going to put your trust into AI and ML for your life, everybody is going to start doubting whether AI ML can be used. Why? Because it has no explanations for the decisions it makes. And that brings the question as to whether accuracy should be the only objective, or reliability, robustness, interpretability, transparency, lack of bias, all of them also are required when you use AI in real world applications. Yes, the system could be getting 95% accuracy, 98% accuracy for that matter, right? But if I was a patient who I'm going to hedge my life on that decision, I'm going to ask, could I be in the 2% where it makes mistakes, right? So who's going to answer me for that? Right? That's the question that becomes important when we talk about explainable AI or machine learning. And obviously that also leads to saying that we need a multidimensional perspective to solve problems in this context. So do existing machine learning models solve the problem? Where do they fall short? Let's look at some of the popular machine learning models that I used in practice today, right? You can almost look at them as a trade-off between interpretability and accuracy. On one hand, you have models like linear regression, decision trees, which are very interpretable. Right? Linear regression gives you a weighted combination of variables that leads to an outcome. So if you have an outcome, you know which variable and how much was it weighted by to lead to that particular decision. Decision trees give you if-then-else rules that you can directly interpret. Unfortunately, they're not the most accurate systems when it comes to real-world data. On the other hand, you have models such as random forests, support vector machines, neural networks, which are very, very accurate. Unfortunately, are largely black box and cannot explain their decisions. So what do we really need when we talk about explainable AI here is we want to push the frontier towards the top right. We want highly accurate models as well as highly explainable models when we make these decisions in complex real-world systems that could be safety critical or risk sensitive. So what are people doing today? Right? So just to summarize a few of the efforts that the community, machine learning research community around the world is doing. Obviously, this is only starting. There are lots more to do, but everything has to start somewhere. And this is just a summary of the landscape of what people are trying to do here. So one broad category of efforts in general machine learning is to be able to get an understanding of how important a given feature was on an outcome. Okay, this is also called feature attribution or feature importance. Is if I have a patient and I've predicted the risk for this patient being COVID positive is at a certain value, it would be nice if the model also said I'm saying this because of this thing in the blood report and this thing in the patient's family history. Right? That would really help a person take action. Similarly for, say, genetic history, or similarly for any other safety critical application. In this context, there are methods such as LIME, LRP, deep lift, integrated gradients, smooth grad, SHAP, deep SHAP. Many of these are used today by companies to be able to explain machine learning models. Not that they are perfect, but there are models out there today that can help you get a sense of how well a particular feature attributes to a certain outcome for a given individual. There are autoencoder based methods, and there are also what are known as surrogate model methods, where you use one machine learning model to predict and a surrogate machine learning model to explain the prediction of the first model itself. From a computer vision perspective, there are methods such as CAM, GradCam++, also some of the ones that we talked about on the earlier slide, SmoothGrad, IG, so on and so forth. And all of them try to help answer the question, if a convolutional neural network predicted a cat in an image, which part of the image was it looking at while it called it a cat? Was it looking at the grass in the background, or was it looking at the cat? Same thing in COVID. If a convolutional neural network was looking at a chest X-ray and said this patient is likely to be COVID positive, which part of the chest was the model looking at while making this prediction is what people in computer vision try to do in this particular context. A similar thing with people in NLP, natural language processing, which part of the document, which part of the email, which part of the web page was this model looking at while it made a particular prediction on a document or a tweet or a review or any other text kind of data. People have been looking at from other perspectives too, from a robotics perspective, from a planning and scheduling perspective, knowledge and representation reasoning, multi-agent systems, search and constraint satisfaction, game theory. A significant part of this work, maybe about more than 95%, has been done in the last 5 years, since the need for explainable AI started becoming more and more apparent. So for if one had to categorize all the methods that people have come up with for explainable machine learning, you could categorize in a few different ways. One family of methods are post hoc methods, where you have a machine learning model and then you use some other method to explain the predictions of the already learned model. These are called post hoc models. They work well because you don't need to change what was already done. You already have a model. You can just add a layer on top to explain its decisions. On the other hand, what is more desirable are anti-hoc models, where you bake the explanation into the learning of the model itself. Example would be decision trees, where the tree gets learned as part of the learning the model itself. Unfortunately, decision trees don't work well in practice. So we ideally need anti-hoc models even for deep neural networks. The other kind of methods are model agnostic versus model dependent. Model agnostic, as the name says, are models which are independent of the machine learning model underlying the decision making. It could be a support vector machine, a neural network, a boosted ensemble, random forest, and the method will work on any of these methods. That would be model agnostic. And similarly, you also have model dependent methods, where you have methods to explain the decisions of specific machine learning methods like SVMs, like convolutional neural networks, like recurrent neural networks, so on and so forth. And thirdly, another kind of categorization of these methods is global versus local, global explainability versus local explainability. In global explainability, you're trying to explain decisions on an entire population. You're trying to say that generally, when I look at a patient and say they are COVID positive, I would be looking for maybe their blood group, maybe their family history, something like that. Right? A local explanation is an explanation for a specific individual. For this patient, the machine learning model made this decision because of this particular reason in the patient. Right? Both have their value. Right? Global explanations are probably important for governments and an entire hospital organization. And local explanations may be important for that specific patient or that specific user in a given setting. Right? Everything has its place in the entire industry ecosystem. So this entire conversation has developed into a new conference organized by ACM, it was initially called FATSTA, but it's today called FACCT, which stands for Fairness, Accountability, and Transparency in AI. So this conference brings together AI researchers and social scientists to discuss these issues and come up with solutions. So this entire area is also sometimes called FATE in AI. FATE stands for Fairness, Accountability, Transparency, and Ethics. And there is no more bigger platform for FATE than in the Industry 4.0 setting, especially in complex pipelines. So I'll take the next 5 minutes perhaps just to talk about some of the efforts that we have done at IIT Hyderabad, and then I'll stop for questions. So we have been looking at several perspectives to explainable AI here. One of the directions which we believe is extremely important is to look at it from the perspective of causality. So if a patient goes into a hospital and say with symptoms of heart attack, and it's likely that the patient's blood pressure will be elevated at that time, right? But does not mean that an elevated blood pressure caused the heart attack. An elevated blood pressure may just be correlated with the heart attack, right? So the question then still means what? But then elevated blood pressure would be something, an indicator of say a heart attack. But we still need to find out what was the cause for that event. Right? So it's important to be able to look at explainable AI from a causal perspective, especially in manufacturing. If you talk about predictive maintenance and prescriptive maintenance, it's not important to talk about saying that a certain thing correlated with a certain observation in a manufacturing pipeline. What caused the defect is perhaps even more important from a company's perspective to address it in that setting. Okay, so that's something that we've been working on. We've been looking at visual explanations and images. We've been looking at common sense reasoning. We've also been looking at the intersection of explainability and adversarial robustness. I'll quickly skim through some of these contributions and I'll stop for questions. One specific work that we did was called GradCam++, where we tried to explain the decisions of a convolutional neural network while it was looking at images. We looked at the limitations of previous methods, which particularly failed when there were multiple objects in an image. And then we came up with a method to be able to weight the gradients of a neural network in coming up with the explanations at every pixel for a given neural network. I'll skip the math here. We end up getting some closed form solution, which turns out to be easy to solve. And using this approach, we show that the explanations that are obtained by our method for a prediction of a CNN more closely matches human intuition. We show that this result can be useful for object detection per se, or can also be used in video-based explanations. So if you're looking at a video and you want to say, why did I say that this player was playing a pull shot? Right? So then you want to say that I'm looking at this frame and I'm looking at this particular pose of the individual, and that's why I'm calling it a pull shot, is what our method can add to while giving that decision. So our method is publicly available, and it actually has been used by people around the world for explaining COVID decisions, for finding defective cells in solar arrays, for explaining cancer prediction and gene expression data, and many more. Another direction that we have been looking at is what is called visual question answering and reasoning, where given an image and a question, our system can give an answer to the question based on the image and also generate a rationale for that answer. So our philosophy comes from the fact that whenever we answer a question, sometimes we think of a reason before giving an answer. Sometimes we answer impromptu and then think of why we said that and refine our answer. So we come up with a model where we first generate an answer, then give a rationale for that answer, then based on that rationale, refine the answer, and then refine the rationale. Right? So this is an LSTM based framework. I'll show you some sample results here. So if you look at the top left result, you see here, this is an image from a movie. And the question asked for the model is, why is person one covering his face? The answer generated by a model is, he's trying to avoid getting burned. The counter question is, why are you saying that? Explainability, right? Important. Then the model says, there is a fire right in front of him, right? So these answers and rationale that you see here are completely generated by the model, right? So you want an answer that is generated by a machine learning model, which can also give you a reason for why that answer was generated, right? So you could again use this for, think about this from a COVID perspective or a manufacturing defect perspective or any of those perspectives. And the last thing that I'll talk about is our work on causality in machine learning, where we try to come up with giving feature importance from a causal perspective. Right? So as I already mentioned, correlation and causation are two different things. This is a statistic from a certain Bay Area in the world where ice cream sales and shark attacks have similar curves. If you now gave both of these to a machine learning model, the machine learning model will think that whenever ice cream sales increase, shark attacks can happen, right? So which means if you eat an ice cream, you could get attacked by a shark. But there's nothing causal about this. This just happens to be a set of correlated data, right? So how do you then identify what causal relationships are learned by a neural network, right? So this goes to some mathematical principles based on structural causal model, viewing a neural network as a structural causal model, and then we define something called an average causal effect of each input feature through the neural network. And then we find a way to solve this using a Taylor series expansion of the average causal effect. I won't get into the math here, but I'll just show you one result that we got on aircraft data. And on a real world aircraft data, this is public data shared by NASA, where we see a bad landing of an aircraft and we want to find out why did that bad landing happen. Okay, so if you see the top left here, the x-axis denotes the last 1,000 feet of landing and the y-axis denotes the different variables, and the blue and the red denote the causal effect of that variable. Red means higher causal effect, blue means lower causal effect. And our model showed that these attributes here, pitch, roll, latitude, and longitude, were the reasons, causal reasons why this aircraft had a bad landing. And it happens that even the FDR report for that aircraft actually agreed with the causal attribution of our model. In fact, we compare it with the other models and show that none of them are able to give such a causal attribution for that particular anomalous behavior. Right? If you're interested, this work is also publicly available along with its code. So let me conclude by then asking what then should we do from an AI perspective for explainable AI, right? So unfortunately, the very formalizations of machine learning are not driven for explainable machine learning, right? So they're all driven for given an X, predict a Y. Nobody talks about predict a Y hat, which is an explanation, right? So how do you come up with standard formalizations fundamentally for explainable AI is a fundamental problem to solve for the community. How do you balance the accuracy versus interpretability trade-off, right? It happens that more the model is accurate, it seems to lose out on interpretability. How do you balance this? Is interpretability always required? Is also a question to ask, right? There could be scenarios where explainability is not required. It's also important to separate and identify those. It's not just because it's a hammer, you don't have to use it everywhere, right? You have to also know where to use it. How do you evaluate explainable systems? The previous speaker talked about testing. Extremely important, right? So even testing AI itself is now rudimentary. How do you test explainable AI? If it gives a reason, how do I know whether the reason is valid? How do I know whether the reason is correct? Right? It becomes important to talk about in this scenario. Who owns the explanation? If a model gave a wrong explanation, was the prediction wrong or was the explanation wrong? Who made the mistake? Who will the company sue? Becomes very, very important problems to discuss, especially when these things get deployed in the industry. And finally, from a technical perspective, can we bring together what historically were different directions, connectionist and symbolic AI, to solve the explainable AI problem? Okay. So I'll just cycle back to what I started with, and maybe just considering this is an inauguration of a new university, go back to start by looking at, if you look at the Industrial Revolution timeline, we had Industry 1.0 in the 1800s, Industry 2.0 in the 1900s, and Industry 3.0 in the late 20th century. And Industry 4.0 has already come. The question to also ask is, the timelines between the industrial revolutions are shortening. What next and who is also a question to ask. And I do hope the new university that's being developed will be the precursor for the next generation Industry 5.0, if I can call it so. I know Japan calls it something called Society 5.0. I once again congratulate all the organizers for the inauguration of the university and all the administrators, and hope that the next generation solutions will come from this university. Thank you, and I'll be happy to stay on for questions.
Thank you, sir. It was a great talk. And there is a question. Would you perceive a protocol for explainable AI in all products in the near future?
I think that's a very good question. So that's in some sense one of the points that I mentioned towards the end, which is unfortunately there is no existing protocol for explainable AI. Right. So just as the previous speaker said that there's no existing robust protocols for testing, very similarly for explainable AI too. So in fact, as I said, the fundamental formalizations of machine learning itself don't fit explainable AI. Right. So if I can go a little bit mathematical here. So the very foundations of learning theory in machine learning and AI talk about, if you look at supervised learning, they talk about a tuple X and Y, right? So all the formalizations of machine learning come from there. X is all the formalizations of supervised machine learning, right? So X is data, Y is label. But clearly, when we say explainable AI, we are saying we need something more than Y. We need something more than the label. We need a reason for the label. So which means even the formalizations have to change, right? So I personally think it needs more deliberation. A lot of the work that has happened over the last few years are more patchwork. Right? We've looked at existing models and somehow tried to see how can we patch a layer on top and try to say, how can we explain that model? Right? It has its own place. I think it's serving its own purpose and it is useful. But I also think we need to also be looking at more fundamental approaches to deploying explainable solutions in the future. Having said that, I think there are existing methods that one could use, but I think everything has to start with data sets. So if you look at the data sets around the world today, all data sets, if you look at supervised learning again, they'll give you data, they'll give you labels, right? But then unless data sets start embedding explanations, there is no way for researchers and developers to even check whether they can come up with methods that can satisfy the expected explanations, right? So I think it needs to start in the creation of data sets itself, where we also embed explanations in these data sets. I personally think that's where the protocols should start to be able to come up with the entire pipeline to have an impact finally at deployment.
Thank you, sir. There is another question. Rat level, host level, or human level AI, what is intelligence and how to explain it?
Just a moment, let me look at that question too. Rat level, host level, what is it? Okay, that's a very fundamental question. And I don't think we are looking at explainable AI from that perspective. At the end of the day, I think the way we look as technologists, as perhaps students, the way we look at intelligence is how can it help improve quality of life, right? I think that's all we look at intelligence for, right? So when we look at AI systems, when we look at robots, at the end of the day, while there is a fundamental scientific pursuit to understand how humans operate, to understand human intelligence, but I think at some level, the hope is that this understanding will also help us improve a quality of life in some way, right? So I do think at the end of the day, be it rat intelligence, horse intelligence, human intelligence, on one hand, we want to understand these things, but I think from a technology perspective, we are looking at finally, how can this improve our quality of life?
Thank you, sir. And there are so many questions in the queue. I think they can email the question as we are running out of time.
Sure.
Thank you for the wonderful session, sir.
Thank you again for the interesting session, and congratulations again for the new, for the new university, and best wishes for its success.
Thank you very much, sir. The next session will be handled by Professor Axel Sikora on the topic Internet of Energy, a view from Good Old Germany. Professor Axel Sikora holds a Master of Electrical Engineering and a Master of Business Administration, both from Aachen Technical University, Germany. He has held top positions in both industry and academia. Since October 2019, he is also affiliated as Professor to Technical Faculty of Freiburg University. His major interest is in the field of efficient, energy-aware, autonomous, secure, and value-added algorithms and protocols for wired and wireless embedded communication, with a strong focus on primary communication, gateway solutions, and data analytics for cyber-physical systems. Dr. Sikora is the founder and shareholder of Stackforce GmbH, an independent and successful spin-off engineering company around IoT connectivity solutions. He is author, co-author, editor, and co-editor of several textbooks and more than 250 papers in the field of embedded design and wireless and wired networking. Amongst many other duties, he serves as chairman of the annual Embedded World Conference, Nuremberg, the world's largest event on the topic. On behalf of KUDSIT, I invite Professor Axel Sikora to deliver his talk.
Yeah, thank you very much for this kind introduction. I hope you can hear and see me and also see my slides.
Yes, sir.
Fine. Yeah, very warm welcome from Germany, where I would like to give an overview of some of the trends which are currently going on in the field of Internet of Energy. And in addition to the original title, when I was compiling the slides, I thought that maybe the original title is a little bit falling short. So maybe it's not only a view from good old Germany, that means a very traditional energy market, but in some respects it's also old good Germany, because sometimes it's old, sometimes it's good. Having said this, let me shortly give the structure of my talk. Let me start with a very short overview of where I do come from, then talk about smart grid, smart energy topics, then give a short history overview of the background where communication and internet-based solutions for the smart grid came from, give a short overview over the multitude of technologies that are available on the market in research and where we are active here. Then, of course, security is a major issue around Internet of Energies, and connected to the security, also some discussions go around the blockchain integration into the IoE. Finally, what we also see is another trend that the Internet of Energy, the smart grid, is increasingly integrated into the normal Internet of Things, and I will have a few more aspects on this. And finally, I will conclude with a summary and a outlook. When I was compiling the slides and inserting also the nice logo of the new Digital University of Kerala, I digged into my old photos. The first time I was in Trivandrum was back in 2012, visiting the IIIT MK. Then there was another visit in 2018. And unfortunately now in this year, it's only a virtual visit. My background or my location is in Germany, which is just in the very middle of Europe, where we are located close to the borders to France and Switzerland, in a very nice region, which is, as soon as you go out of the cities, you are in the middle of the nature. In summer, it is very greenish. Just this winter has been extremely beautiful with lots of snow. So the lower pictures are just made 2 weekends ago. And the region is called Black Forest. And when I was in India, in the hotel in Mysore 3 years ago now, every morning I walked along the sweet bar and saw a black forest cake. So this is a very traditional cake that comes from our region. That means whenever you run into a black forest cake, please remember the beautiful black forest that we have seen on the slides here. Scientifically, my background is in an institute of reliable embedded systems and communication electronics, where we are very much involved in stack development. That means stack standardization, specification, but also in the implementation of the protocol stacks, including the test and verification. And throughout the course of this presentation, you will see some examples of how we implemented and tested novel protocols, especially for the Internet of Energy. In doing this, we spend lots of efforts in a very reasonable hardware-software co-design. That means balancing the efforts between hardware implementation in an FPGA, for example, or the software, the firmware in the microcontroller. This especially is crucial when it comes to embedded security, which is also one of our major topics. And when we are talking about security, then also the attacking side and the data analytics side is crucial. In parallel, I'm also working at a research institute, 50% of my time. It's called Hans Schickhardt Association for Applied Research, where in the institute, we have the complete value chain from microtechnology over MEMS, sensors and actuators, down to software solutions and cyber physical systems. So basically we can cover the whole value chain from the sensor to the cloud, where my responsibility is heading the software solutions division. That means we are covering with my team of about 20 engineers and senior engineers the C part of the cyber physical systems. As mentioned, I'm also heading a spin-off company which is relevant in this field of Internet of Energy, where we do embedded connectivity solutions for several protocols that will come and that I will discuss in the remainder of this presentation. So let's go into the topic itself. Obviously, the Internet of Energy is one of the prominent candidates for the Internet of Things, where the multitude of producers and consumers need to be interconnected. And the more diverse the energy sources become, the smaller the power plants become, the more prosumers we have, that means combined producers and consumers, the more intelligent the network needs to be. And when it comes to intelligence, then speaking, listening, understanding others is of key importance. So it is my very simple belief that the smart grid also needs smart communication. All the aspects that are around sensing are nice, but also only give local or deliver the local information, but not information from other places, from other sensors, from other locations and systems. So communication increases the possibility to have the full picture and make reasonable, intelligent decisions on the spot. If we are talking about communication in the smart grid, typically we talk about 4 levels of communication. We talk about the primary communication between the meters and a gateway, a controller. There might be a secondary communication between the meters or between the meters and some display elements. Then we have the tertiary communication, which connects the gateways with the backend system, and then there might be a 4th level, a quaternary level of communication between the backend systems and the consumers, or between different backend systems. From a research point of view, it is especially interesting to talk about the primary communication or the smart grid communication, or something which is called the local metrological network. Because it's the most demanding, because on one side it comes with extreme cost restrictions. Meters, electricity meters, or also water meters are being sold at a cost or price point of several euros, maybe 10, 15 euros, which translates to 100 to 200 rupees. So we don't have much resources with regard to computing and memory. Also, and this adds to the price point, ultra low energy is another requirement, especially when it comes to water and gas meters, which are battery powered. Lifetime of these meters should be in the range of 10 to 12 years from a single battery. So we are talking about extremely strict requirements on energy consumption. And also, the third point, this smart metering primary communication demands for extreme scalability and reliability. That means if you think of an urban area with gas, water, electricity meters, potentially also heat meters over here in Germany, or cooling meters, thermal energy meters on your side maybe, then we have for each household 3, 4, or even more meters multiplied by the number of households. That means easily we come up to several hundreds of thousands of meters or even millions of meters in one municipality. And this calls for an extremely stable scalability and reliability, including also with a high degree of automation, because you don't want to run all these lakhs or millions of meters manually, but from an automated system. Talking about these big numbers, it's not only technical requirements, but it's also market requirements, where most of the utilities don't buy with only one vendor, but from different vendors to avoid vendor lock-in. So typically you have at least 2 or 3 vendors in a network, which means that we need standardization. Also, taking into account the different aspects of the utilities of the Metering, Weights and Measures Act, of the international aspects. There are lots of different associations active, and I will shortly mention this in a second. What is important to understand is that this metering or smart grid communication is not only interesting from the scientific point of view, but also from the economical point of view. And in order to open the market, the European Union has opened this market. So already 12 years ago, there was a third energy package, which was mandating an interoperable EU smart metering rollout. And even though this decision was taken 12 years ago, it is only now that these rollouts really start to be implemented. And if we are talking about interoperability, there are several institutions and associations looking after this interoperability. For the smart metering part itself, it's mostly the OMS looking after the physical interoperability, and these standards are then taken over by Senelec on a European level to make them subsequent ETSI standard. So apart from being involved in engineering work, association and political work is the issue. One of the cornerstones is the so-called MBus, the metering bus protocol, which exists in a wired and a wireless specification. This was a very old protocol back in 2007. It was a historic document. And then in the OMS, the Open Metering System Group, we made a clean specification out of it, took out many of the options, having also left in many options, and made a clean structure out of it, so that implementations can be very well organized, hierarchical, stack implementations. This picture shows our implementation of the OMS implementation, which is offering all the different versions for all regions worldwide. So a very modular approach. This modularity is especially important because there are different modes here for different frequency regions, for different modulation schemes, and different access schemes. So this is highly flexible and to meet the different requirements. And this flexibility is extremely important because especially the development for the wireless world is advancing rapidly. One of the recent trends, and I know that also in your region you have lots of activities around this, is the upcoming of narrowband technologies, low power narrowband technologies, where we might achieve link budgets of 140 dB or more at low output power and at low cost. So having these long range communication is not a novel trend, but having long range communication at low power and at low cost, this is novel and opens completely new applications, because we are now spending for a wireless node not 10,000 rupees, but maybe only 500 rupees. So this makes a difference, and the lower the cost, the lower the energy consumption, the larger the number of applications which can be served with these technologies. Basically, there are two technologies behind these low power wide area networks. One is going to the direction of adding additional encoding schemes to improve or to enlarge the process gain. That means we add redundancy to increase the link budget. The other approach goes for ultra narrow bandwidth transmission using ultra slow modulation of several hundreds of bits per second, so that you have enough time to accumulate, to integrate the incoming power over the noise. Both approaches exist, and we'll see the solutions in a second on the next slide. Let me also mention that there are two basic approaches for supporting these narrowband technologies. One is called the 0G, or what I like to call short-range wireless networks with long range. So basically taking the architecture, taking the solution of existing short-range wireless networks like Zigbee, like wireless M-Bus, or like Z-Wave, and just replacing the physical layer with long-range communication. In these local or short-range wireless networks, network management, security management, also node management can be very simplistic. So you don't have much overhead from that side. The other direction that we see comes from the cellular communication, where in the past the development path has always been towards higher bandwidth. Interestingly, 4G already introduced the narrowband IoT version in order to have reduced bandwidth and a slightly simplified node and network management. That means no handover, possibility to use eSIM, and so on. If we look at the existing technologies, we see this overview from public to private and vendor-specific to open standards, where the narrowband IoT version uses public networks in the cellular field as 4.5G communication. Sigfox is a 0G technology, nevertheless offering public networks. LoRa and LoRaWAN is vendor-specific and allows the setup of private networks. And IoT is a upcoming solution, which is an open standard, but allowing also private networks. Let's go into a little bit of detail because I believe it's kind of interesting, and maybe you guys are also working on these technologies. LoRa, as I said, is a proprietary technology by a US company with a strong foothold in close to our region in France. in Grenoble, where this technology has been developed for a specific modulation scheme, which also allows flexibility. That means you might trade off bit rate versus range. That means the larger the range, the lower the bit rate. And if we are talking about bit rate, it might go down to a few hundreds of bits per second. The range is really as big as promised. So this is not really, or not only marketing propaganda, but from real-time measurements or real-world measurements in our region. Our university is in location A. We see that indeed several kilometers can be covered from a single node with an output power in the range of 0 to 10 dBm. That means between 1 and 10 milliwatts. Maybe a few examples of what could be done here. These are installations of underground water meters in our neighbor city, which is called Freiburg, where the normal readout mechanism is going down into the shaft, reading out, and then coming up again and make manual type in. This is time consuming and dangerous. Now we have a two-level communication with a local communication between the meter and a gateway, and then the gateway is connected via LoRaWAN network to a central database, where in a city of 200,000 inhabitants like Freiburg, there are only 7 base stations to cover the whole region. The complexity is very reasonable. That means if you look into the implementation of the LoRaWAN stack, that was, by the way, implemented by our Stackforce spin-off company, then you see that it's only a few kilobytes of code which is required if being implemented in a diligent way. Another alternative is the Sigfox, where we are rather going into the path of very slow modulation and public networks. That means Sigfox is a service provider and mobile network operator, which has defined an own modulation scheme, which is based on a little bit tricky phase modulation, which is so slow that you can do it on a reasonable ARM Cortex-M3, M4 microcontroller. That means you just take any transceiver operated in the base idle mode, and then do all the phase shifting through the software on the microcontroller. So software-defined radio in a very simple but tricky way. Again, here, Stackforce made an implementation based on the university research, and also here, the stack complexity is very reasonably small. Coverage in our country is very good. Red means very good coverage of 3 base stations and more. And if we look into our city, where our university is located down here, also in this region, we have nice coverage. And then as a recent contender, we also see MyOT protocol or MyIoT protocol, which is using a frequency hopping scheme or telegram splitting scheme, a little bit like Bluetooth, but with some additions, because there are no preambles and no synchronization phases for the different frequencies, but everything goes into one single telegram, which is then splitted over the frequency channel, which allows very high stability and interference resistance. And finally, there's also the narrowband IoT protocol, where we especially see narrowband IoT in the release 14 and 15 for the German market. Taking all these standards, where partially we are also involved in the standardization or the feasibility studies, we see that there is a lot of parameterization, lots of optimization, and for this we have developed a very nice test environment, which includes lab tests based on base station emulators, which includes emulating the RF channel, but which also includes free field tests outside. Everything being automized, that means most of the tests nowadays are just push button tests, which run completely automatically. And with this, we can do lots of performance measurements and assess the quality and the stability of the different protocols. Let me mention another aspect apart from the long-range communication, which is mostly a cost issue. The other one is security, where security, of course, is if you read in the textbook, defined as a state without dangers and risks or with a sufficient protection against those dangers and risks. That means this guy here exposes himself to dangers and risks because, well, power is still on, and he does not even take any countermeasures. If we are talking about IT systems, you either don't connect your IT system or you take appropriate countermeasures. And this especially is important for the smart energy world, where we have different security levels. That means ranging from 1 to 5, we might have incidents which only affect the town or the neighborhood, but this goes up to highly critical incidents where we have even a pan-European incidence in the in the interconnected energy network of the European countries. And having said this, it becomes obvious that energy networks are critical infrastructure and therefore need to be secured. One of the directions that we see here from the old good Germany is the technical specification or technische Richtlinie TR 03109, which also has been developed with our support, where this directive mostly goes into the direction of the smart meter gateway. This directive has been issued by the Federal Office for Information Security, an agency which is under our Ministry of Internal Affairs, and this federal office plays a major role for doing or for developing specifications for IT security. Very reasonable, very good work that they do here. And in this case, we have specified with them this architecture which has the smart meter gateway as a central element, as a trusted node, which connects the local metrological network between the meters and this gateway. The gateway is then connected also to the wide area network, to the backend systems, and it's also possible to have a home area network with controllable load systems like solar, photovoltaic PV stations, combined heat, electricity stations, electric cars, and so on. What is interesting is that for all these communication flows, it was mandated to use the TLS protocol, Transport Layer Security, that you know also from HTTPS. That means from the normal IT world. And when we started the specification, everybody was very nervous, claiming that TLS cannot be mapped to small microcontrollers, cannot be mapped to low-end communication. But nicely, our demo installations showed the flexibility. So implementation now is on the industrial side, and what we are currently doing is testing in our test bench. So what you see here is, of course, smart meters, and also two of these smart meter gateways, which include a trusted platform module, which include the local communication to the meter, and then the wide area communication over cellular networks to the backend system. Having talked about the security, let me also mention that blockchain is one nice tool to enhance the trackability, the visibility of the transactions, especially in distributed environments where we don't have only one utility, but where multi-vendor, multi-agent setups might come into the game. And what we are doing here is not working so much on the blockchain side itself, but in order to connect also low-end sensors into this blockchain world. So in the end, also low-end smart meters are connected to the blockchain, ensuring the reliable input into the blockchain, because obviously for the blockchain applies what applies for many other databases. If you have non-reasonable input, then you also have non-reasonable output, or shit in, shit out. So it's extremely important to have a reliable and efficient, also cost-efficient integration of these low-end sensors directly into the blockchain. This is one of the directions that we take. And maybe as a last point, let me also mention that this energy part that I've been discussing now is being extended in the OMS, the Open Metering System group, where we are also deeply involved, has opened a task force sensors to integrate additional sensors for smoke detectors, occupancy sensors, and the like, to make a first step towards home automation and building automation using the same communication protocol for the upper layers, but then also being flexible for the modulation schemes on the lower layer. So basically a very modular approach, which is overdue after so many years of communication development. So, making a long story short, I believe that there are very many interesting and challenging and R&D topics around the smart grid communication. I hope that I could show a few of them, and we expect interesting activities for the next decades. One is extension of new physical and network protocols. Security issue is an ongoing task to balance the different requirements of complexity, cost, and real-world implementation. And the third aspect, I believe that the Internet of Energy can be the platform for a much more complete system integration, where we really might not only integrate the Internet of Energy, but the Internet of everything. So let me conclude my presentation. Thank you very much for your kind invitation and for listening to me. If you have questions, I would be happy to answer them now. Thank you.
Thank you very much, sir, for the wonderful session. And now we are sorry to skip the question answer session due to time restrictions. However, the attendees can pose their questions in Q&A, and we will answer it later via email. Once again, thank you very much, sir, for the session.
Pleasure.
We were really glad to hear you remembering the last meet at IIT-MK. Once again, you have delivered a wonderful session for us. Thank you very much, sir.
Thank you.
Next session is on Industry 4.0 and Society 4.0 Challenges from a Data Sciences Perspective, and will be handled by Dr. Ajit Abraham. Dr. Ajit Abraham is the Director of Machine Intelligence Research Labs, a not-for-profit scientific network for innovation and research excellence connecting industry and academia. Dr. Abraham works in a multidisciplinary environment involving machine intelligence, cyber-physical systems, Internet of Things, network security, sensor networks, web intelligence, web services, data mining, and applied to various real-world problems. In these areas, he has authored and co-authored more than 1,300 research publications, out of which there are 100 plus books covering various aspects of computer science. More than 1,000 publications are indexed by Scopus, and over 800 are indexed by Thomson ISI Web of Science. Dr. Abraham has more than 36,000 academic citations, H-index of 89 as per Google Scholar, and has won 7 Best Paper awards at prestigious international conferences. He has given more than 100 plenary lectures and conference tutorials in 20 plus countries. Currently, Dr. Abraham is Editor-in-Chief of Elsevier Engineering Applications of Artificial Intelligence and serves editorial board of over 15 international journals indexed by Thomson ISI. On behalf of Kutsit, I invite Dr. Ajit Abraham to deliver his talk.
Thank you so much. Am I audible? The screen is visible?
Yes, sir, you can proceed.
Okay, all right. So good afternoon to all of you. It is indeed a great pleasure for me to give this talk. I would like to thank the organizing team for putting this digital summit. And congratulations to the team behind the Kerala University of Digital Sciences, Innovation and Technology, which is actually a very timely and a novel initiative in the Indian context. And I hope that it will thrive and be a model to the society and to the country. I guess we are already like half an hour late, so I will try to cut short some of my slides and move a bit faster, because I guess we have one more speaker before lunch break. So I will try to do as much as I can. So please bear with me if I go a bit fast. So today I'm going to give a more general talk about Industry 4 and Society 5 and the role of AI and data sciences. I guess most of you are very familiar with Industry 4. I guess the previous speakers have already talked a bit about that. So I will skip some basics about Industry 4, and I will focus on Society 5 and the role of AI and data sciences. So my quick agenda is Society 5 and followed by data sciences, intelligent computing, and some quick conclusions. So Industry 4 is has been well established, and it has been practiced by various countries around the world. Actually, there are several names used by different countries. You know the core technologies behind Industry 4. And Society 5 is something very similar, but it is more society-oriented. As you know, industrialization, I guess the best of the industrial revolution happened in Japan following the World War II era. But they did a lot of wonderful things, especially in the field of AI, data sciences. They were the first who did the front run. So basically, they are more interested in how these technologies can contribute to humanity, to the society, rather than like automation of things. Basically, they have already automation and robotics in place. So basically, they want to see that how these technologies can help the normal human being or the society at large. So if you compare Industry 4 and Society 5, basically this goes into 5 steps, starting from the birth of human beings. Then they have a separate slot for irrigation, the revolution of various irrigation techniques. And then the starting of using of steam and water power in the 18th century, which is very similar to Industry 1.0. And basically they skipped Industry 4.0, the step 2, that is invention of electric power in the early 20th century. They really skipped that, and they are more focused on the later half of the 20th century, where we had developed computers, ICT, and various other developments. And then what they call is the future is Society 5, where they want to see everything integrated in the society in the best possible way. And as we know that we have several verticals. When you talk about problems, we have several verticals, but they are very sparsely connected. So Internet of Things is believed to connect all these peoples and things, and basically you can imagine a lot of knowledge flowing in different directions. And as you all know that now people like to live in cities rather than villages. And then we have all these population issues. We have aging population in small villages, small cities, and they need care. And it's believed that the Industry 4 or allied technologies will help this class of society and take them to a new world. And again, we have several tough things which are really physically very huge. So basically all this robotics and certain things can help. At the same time, repetitive works, understanding complex data, manipulating information, and finding meaningful things from that. So all these things, AI, data sciences, etc., could help in a very big way in Society 5. And if you look at Society 4, which you see on the left side of the screen, you would see a lot of verticals. Like, for example, let me give you a nice example. For example, you want to buy a new Nike shoes, and you have some specifications. For example, you want certain color with the swoosh line and certain part of the shoe. Probably in the modern society, Industry 4, probably you might have to search for various designs, and then you have to analyze by yourself what is the best color combination, how the swoosh shine, the position would be looking better at what position. And again, you have to customize and go to like a manufacturing plant, or to talk to some company how to make it, and then they have to customize it and they have to get it done. But imagine a situation where we have all these verticals connected. So you search for all these designs, and the system knows that this is what you want, and then the system automatically orders directly orders the shoes, and the robot in the company, they actually takes the order, and the shoes goes into the production line, and basically you get it at home. So basically all these verticals are connected, and you don't have to go through so much of iterations between different verticals. So the basic idea is to make our life more simple and more easy. And as you all know that Internet of Things is going to change our way of living in a very big way. I guess you might have heard from previous speakers, improved performance, you can imagine scaling up of things, reduce cost of various services. Even we can create innovative services. Imagine a situation where you can do things very differently, can create new revenue streams, which are, I think, very important for a country like India, or even state of Kerala. So you can think about various ways to innovate. So hand in hand, cyber-physical systems is another interesting framework. We see a tight combination between the computational and physical elements. So you can see in various diverse application areas, from automotive to monitoring bridges, energy, healthcare, manufacturing, transportation. So basically you see a network of interacting elements with the physical input and output design of as a standalone devices. So basically you see interaction of various devices, and the control happens over the cyber infrastructure. So you can imagine robotic surgery, you can imagine a building on fire, then robots going to rescue, war fighting, augmentation of human capabilities. So basically, you can imagine sky is the limit for such frameworks. And if you think about some practical applications, for example, environment, which is I think very important for India or even for Kerala, it's very important to preserve the nature. For example, if you have sensors which are really very cheap nowadays, you can actually implement various types of sensors. You can detect like smokes much earlier than before the fire really breaks out. You can actually monitor pollution level in the water, in the air, in various facilities. You can actually prevent natural disasters. For example, like in Kerala, you have all this landslides, floods. You can have sensors, and then you can actually have advanced warnings for such natural disasters. Global warming, which is a global problem. Basically, if you have a continuous monitoring of a certain weather parameters, how they're going on for a region, for a particular state, for a particular part of the country, then basically you can actually try to do something so that it won't go really that bad. And then like a state like Kerala, where you have rivers and sea coming in and out, you can also monitor the salt water levels by deploying good sensors. So basically you can have a very I would say very intelligent monitoring by having all these devices. Nowadays, people like to live in smart cities. The idea is to have better living, better services, connecting citizens with the government, and providing all the best utilities at a low cost. So basically, people try to rush to live in the cities because it is a lot better, well-connected, and better affordability to many things. But this also, at the same time, give rises to, for example, traffic, pollution, waste, all these interesting things which we want to avoid. So basically, by having data, by having all this data from various consumers, for example, like cars, for example, like mobile phones, you can actually monitor traffic. You can control traffic condition. You can monitor pollution. For example, if you have sensors to big waste bags or big waste containers, you can actually monitor how the wastes are moving from one place to another place. You can actually control transportation, real-time channeling of transportation by optimizing water supply networks. You can actually monitor the crimes at real time. You can actually provide very interesting community services to take the government responsibilities to a totally new level. You can actually use all these technologies for healthcare, from continuous care to surgery-related to neurological disorders, for example, like Alzheimer's, Parkinson's, to monitor sportsmen. So basically, I would say, sky is the limit when we look at all these technologies, IoT, artificial intelligence, big data, and various other frameworks coming together. Like sky is the limit to innovate. For example, there are a few apps, for example, like the Heal, which is a very interesting framework. By touching at your mobile app, you can actually find a pediatrician in the city, the best pediatrician in the city, according to your requirement. Like Okin is another app which actually translates unstructured data sets to accurate diagnostics, and even you can predict that based on this voice or this pattern of voice, this particular patient might have Parkinson's, or probably based on this cough, probably this patient might be having probably symptoms of COVID-19. Similarly, DeepScribe is another interesting app. It actually translates in real time conversations to medical notes. So imagine, like usually, transcriptions, usually it is very difficult for people to take note. But imagine if you have a machine to help, it can save a lot of energy. At the same time, it can also improve the performance for future. Similarly, Limbix is another platform which actually helps patients to improve their situation or condition with virtual reality. So imagine all these, situations giving to patients and clinically, tested and clinically monitored virtual reality situations. They can help the patients in a very big way. And nowadays, wearable devices are very cheap, right? You can actually buy devices and put in your arm, put on, wherever you want for various monitoring. You can actually track your sleep. You can actually monitor your sleep patterns, how much time you're awake, whether you're restless, whether the sleep is continuous. And imagine if you can link this with your mobile phone. For example, keeping a track where you're going, who you have interacted with, how long you have been speaking to your friends in real time and in chat, various apps, and how long it takes to get to work. So all these things, if you put together, it can help a lot of things, from personal development, healthcare, to planning, various things, etc., etc. Similarly, e-commerce is another big area, from shipment tracking. Basically, you can monitor how your shipment is going through, or containers, how they are managed in ports, to various trucks and how it is going to various storage places. Supply chain management, the whole chain, and then inventory, managing inventory, having the right amount of stock. So you can imagine it is getting more interesting, and it will only get more interesting. We developed an app, in 2008, we developed a shopping agent. So basically, if you have this app in your phone, and once you get into a shopping mall, you can imagine, your mobile phone is connected to various shops, and they find offers, and then they try to find, the best offers. And 12 years ago, the situation has changed. Now, IoT and various low-cost technologies, things have changed a lot. And now, probably your dresses might have smart sensors. And imagine if you have such smart sensors, once you enter a shop, that particular, that you can get the feedbacks telling that probably, there is better offer in some other shop. Don't go for this shop. Or you can even negotiate, with some other shop and find whether this is the best place, or whether that is the best place. So you can imagine all these verticals connected in the best possible way, and all these things are automated now without much human interference. From payment, for example, you don't have to take a card. Probably it will talk directly to the reader, and then it will make the transaction. And once the product is bought, then a new product will be put back in place. Imagine, if you have milk in your fridge, and you consume the milk, and somehow the message goes from the fridge to the delivery store that you need 1 liter of milk, or 1 bottle of milk, because you have already exhausted the stock. Similarly, you can imagine, looking at the mirror, you can imagine you need a haircut, or looking at the mirror, you're seeing that probably it is cold outside. Probably you need a better a better selection of clothes to face the cold outside. So you can imagine various applications by having all this digital transformation and making use of these technologies. And I would say especially the tourism industry is a very nice industry where we can do a lot of innovations. Basically, most of the tourists, they are using a lot of mobile technology, from booking tickets to finding the best places, finding hotels, finding roads, finding the places where they want to visit, etc., etc. And imagine if you have augmented reality, enhancing those touristic places, and marketing that to attract more tourists, and using IoT and various devices connected together, giving them real-time recommendations, real-time feedbacks. Virtual assistants can also guide them in the process. And of course, making use of this niche of tourism data, that is very important. And I guess that is something which is very very nice to do a lot of promotions, to know what demands, and we can actually provide the best recommendations according to the need. So I will move from applications to technology. So I talked about a lot of different applications, At the same time, when you talk about all these applications, it gives rise to what you call as a big data. So we need to deal with volume of data. We need to deal with different types of data. We need to deal with uncertainty in data. For example, like in networks, when you have wireless networks, sensor network beds, certain networks, we're not sure whether the data comes from that particular sensor itself. So we need to deal with veracity besides volume and certain other, regular aspects. And there are, like various frameworks. Thanks to big data technology, it's a very mature platform, almost 15, 20 years. So nowadays we're dealing with, almost like zettabytes of data. It's beyond imagination. So if, for example, I was involved in a very big supercomputing center, and the center itself is almost like a 4-story building. So you can imagine the size of a supercomputer handling such massive amount of data. And basically we need to customize several AI methodologies, big data technologies to understand the data depending upon what type of data. Many times when you deal with unstructured data, for example, if it is graph, for example, if it is you want to analyze a part of Facebook, where you have probably several millions of people, and you want to analyze what is going on in this particular graph. So probably you need to deal with totally different types of AI methodology, the data structure to read, to understand such complex graphs. It could be text, could be weblogs, could be multimedia, could be video streams, could be voice messages. So you can imagine, depending upon what you're getting, you need to deal with various methodologies. And in AI, we call it's all about understanding patterns. For example, if it is understanding a human face, or you want to use biometrics, understanding iris, a signature, you want to see how the person walks, you want to understand fingerprints, you want to understand the way a person speaks. So basically, if you can understand all this, that can translate to what you call as intelligence. And to put it more scientifically, we can categorize problems into several classes. For example, functional approximation deals with regression, classification, pattern recognition. So for example, given number of COVID patients today, what will be the number of patients tomorrow? Okay, it's simple classification, simple regression problem. Likewise, classification, you want to classify, genders, or even some animal groups. Similarly, clustering is another nice problem in AI, where we try to group similar looking objects together, and objects that are different, we try to keep as far as possible. So the inter cluster difference as far as possible, and the intra-cluster difference as close as possible. Approximate reasoning is another important tool in AI, and basically we need that to manage uncertainty and imprecision. Many a time, we cannot work with a crisp world. We need to deal with uncertain imprecision. So we have various building blocks to deal with uncertainty and imprecision. Similarly, optimization is another huge area within AI, where we need to find the best parameters. For example, what is the best shape of an aircraft wing? Or what is the best shape or the best parameter for designing a valve? Okay, or what is the best shape, or what is the best way to load a truck? You have certain amount of volume of cargo, and what is the best way to load that? So basically, you can actually build some blocks, like certain tools are there for certain tasks. For example, neural networks, subroutine machines, or deep learning types of machines for dealing with approximate functional approximation. Then we have all this meta-heuristic method for dealing with search. Then you have fuzzy logic, rough sets, near sets, various other set theories, probabilistic reasoning to deal with the whole group of approximate reasoning. And basically, if you look at like neural networks, I just want to go a few more slides, a bit more into deep into technologies. So depending upon the number of neurons, you can see the way we can categorize or where we can predict. So the boundary between classes. Okay, so number of neurons, it actually determines how well you can make the boundary. And there are several works. For example, you can optimize the boundary. For example, if you use evolutionary neural networks, or using some meta-heuristic methods to tune the conventional neural network, or or sometimes you have the problem of you need to deal with complexity versus accuracy. You have a big network, but probably it's not very, it is very accurate, but probably application cannot handle such big network. You need a small network, but probably you can compromise some accuracy. You can have a trade-off between accuracy and complexity. So we have done some work in these areas. Another huge area is the field of approximate reasoning. Fuzzy logic deals with imprecision and uncertainty. And for those who are very familiar with expert systems, basically we need to put a lot of hands-on. We need to desire the input-output variables, relevant fuzzy inference system, the membership function, how to build a knowledge base, later how to fine-tune them, etc., etc. And there are several frameworks for optimizing such approximate reasoning models. Neurofuzzy models were one of them. And I just want to give a quick snapshot how neurofuzzy system could perform when compared to a conventional neural network, etc. So basically, you can see that a neurofuzzy system could work a lot better than a typical neural network trained using conventional learning methods. Similarly, you can also optimize for the system using evolutionary methods. And basically, if you use evolutionary methods, you can see that it is a lot better than a neurofuzzy method, and of course, a lot better than the conventional neural networks. And one advantage of a fuzzy system is it is very interpretable. You can actually define, you got the results because of this. If data or input 1 is like this, input 2 is like this, then your output is like this. So you can actually explain your results in a much better way. And basically, you can also have the problem of complexity and accuracy in the case of expert systems. You have a big system which is very accurate, but like probably you cannot handle it in your system because probably it is a mobile device or a sensor. So you might need a small system. Probably it's not so accurate. So you can have a trade-off between accuracy and complexity. So I just want to give a quick illustration. So basically, this is a real-life problem. We had 300 features. So imagine if you have 300 features, to have a fuzzy system, you have even if you have two membership function per input variable, you have 2 raised to 300 rules. Unpractical. So basically, we try to minimize that number of variables to 4 variables, just 4 variables, and you can have a very small model, a very simple model, which can be used in practice. This is a real-world application, trying to use the reduced fuzzy model using a multi-objective model. So to conclude, I would say there is a big convergence between cyberspace and physical space. I guess in Society 5, we won't see that horizontals will be very tightly coupled. And I'm sure AI and big data is going to play a big role in shaping up Society 5 and making our robots work more effectively. And I guess for AI, I guess we have to do a lot of work. We are still learning a lot of things, fast learning, achieving a global error rate, unbiased, with data or with model, computationally inexpensive, which is a very challenging issue. And I guess we also need to spend a lot of time for data acquisition and pre-processing, because that is also very important. If you have the wrong data, then it can actually kill the model, and it is because of wrong data. So I think it is important to spend some time to get the right data to build the right model. So I guess I have a short movie about 1 minute, and after this I'm going to close. So it's a very interesting movie. You can see it is about unmanned vehicles. Sorry, didn't. For some reason, I guess it is not. It's not. I'm not. Let me see whether I can. with that, I will conclude. So that was a recording of a swarm of drones, 3,000 and something drones flying together, creating a world record. So it was, the previous record was 2,000 something. So you can imagine the future is, you cannot imagine what's going to be the future. If you have 3,000 something robots, flying robots going, that can do something, coordinate and do something, I think the sky is the limit for future. So thank you so much. And I wish you a nice summit. So if you have any questions, you can actually, the best way is to email me, or you can actually type it on the chat box. We are also running late. So thanks again for listening to me.
Thank you, sir. Thank you for the wonderful session connecting Industry 4.0 and Big Data Analytics. Audience, if you have any questions, you can post it on the Q&A. So there is one question. Now that K-phone is a reality in Kerala, would you recommend low-range wireless area network for Kerala to give a fillip to all those opportunity area which you have shown as high potential for Kerala?
Sounds very interesting, but I'm not really sure, how well they can implement this using the current infrastructure, because basically we have problems with the infrastructure itself. For example, when you go to remote areas, we have sometimes we have problems with the basic infrastructure itself because of the weather, natural issues. So unless we are able to fix those things, then the technology is on top of that, that will also be affected. So I guess it, of course, definitely it is a nice idea, and I guess we have to hope for the best.
Thank you, sir. Any more questions? Audience have any questions? You can post it on Q&A. I think there are no more questions.
All right. So thank you so much. I wish you all a nice time.
Thank you, sir. Thank you once again for that informative and wonderful session. We are sorry to announce that the next session is cancelled as the speaker is not available. Now we are going for the lunch break. Participants and attendees, please be back by 1:45 p.m. Now we are having the lunch break. Thank you. Afternoon all. Let's begin the session. The next session is handled by Bhaskar Chobe on the topic integrated sensors for the IoT era. Bhaskar Chobe is currently the chair of analog circuits and image sensors with Sagan University, as well as head of microelectronic intelligence in Fraunhofer Institute of Microelectronic Circuits and Systems, Duisburg. In past, he has served with the University of Glasgow, Somerville College, and the University of Oxford. He received the IEEE Sensors Council Gold Early Career Achievement Award and the Merrill B. Reed Best Paper Award from the IEEE Midwest Symposium of Circuits and Systems. He is an associate editor of the IEEE Sensors Journals. On behalf of Kudsit, we welcome you, sir.
Thank you. I will start sharing my screen, which should make life easier. Good morning from this side of the world to all of you, and good afternoon to you in India. I hope my sound and audio is clear. I'm going to talk about integrated sensors for the Internet of Things or Industry 4.0 era. Before we do that, it's worth recalling that the whole aim of an industry is to produce something or to manufacture something. In doing this, we generally need to know the knowns, measure the knowns. This could be your product which you are measuring, the volume of your product, the quality of your product, as well as things which go into making your product. You might need to know about the climate, you might need to know about the market. Sum total, you need to sense something. And once you have sensed something, you then need to predict, the forecast, the unknowns, or what's going to happen. This could be in terms of production factors. It could be what's going to happen with market, how are my raw goods, what's happening to my liquidity, or even something simple. If you're in the farming business, are we going to get monsoon or not? If you are manufacturing it in the business, do I need to do some maintenance upgrades to my machinery? Or if I have got a boiler, do I need to maintain that? So in a sense, we need to infer. And with all of this also goes the idea of we need to secure the whole system. With that as the background, this is what we need to do. I'm going to talk about sensors, but before we jump into the Internet of Things and Industry 4.0 era, it might not be a bad idea just to look at a little bit of history. I know we engineers don't like talking about history in general, but I will give a brief history lesson of civilization, not necessarily limiting ourselves to kings and queens, and also not necessarily limiting ourselves to industry, as would be a typical Industry 4.0 lecture starting from Industry 0.02 onwards. But let's talk in terms of what has happened with electronics, with sensors, with what do we do with the data, and how do we secure ourselves and maintain our privacy. And this will give us some idea about what to do in immediate future. What are things which are happening, which are challenging, and how do we make it better for the upcoming world? So Industry 0.0, which is as old as the human being itself, I think it's more of a nomenclature these days, but this is when the first industrialization of human being happened. We started farming or we started hunting. All of us were engineers. Our hands were primary force, we were tradespeople. The traditional tradespeople were carpenter and blacksmith. As far as electronics is concerned, this is fairly well known in the history of computing. We learned this thing. I think we discovered the number system, which has to be the first aspect of computational activities, which we did. We did have rudimentary counting systems, abacus and other things. The communication was fairly local in the sense that you only talk to people in your village, at max to the nearby village. And there was quite a significant amount of security and privacy. You really did not need to worry about that thing because it was fairly guaranteed. But we were still sensing. It was not as if we were not sensing something. Our primary sensors were our senses, eyes, ears, nose, but we're also building structures to sense outwardly things. For example, astronomical observatories. And in the ancient world, both in India as well as abroad, there were a fairly large number of people who were fascinated with the stars and other things. And we were recording. We were recording primarily nature, but not in a very great sense of thing. There was a very haphazard way of recording, no standardized system. Some scientists recorded their observation and so on and so forth. But what did we use this recording primarily for? When it comes to prediction, we were primarily interested in things like, when will it rain? Will the agricultural crops be better? Are we going to get locusts or famine? And of course, things like wars and marriages. And we somehow were very nicely moved from a very scientific way of observing to fairly unscientific way of prediction. So we somehow mixed the astrologer and the scientist, and we developed a new sense of science from Industry 4.0.0. That would be our prediction ability. Many centuries later, about in 18th century, we start looking at the first industrial revolution starts in England. We have got steam and water power. I think Scottish colleagues may like to object to that, but the mechanization happened and we have division of labor. We have specialized people who work on the work floor, people who work in the bakeries, so on and so forth. And we also have more established birth of cities rather than just village-based thing. People are now moving. They are moving from villages to cities to work in these factories, which also leads to the birth of middle class. Now we have professionals, professional engineers, some of them maintaining these weaving looms and the mills and so on and so forth. Comes to electronics, this was actually a very fascinating era. We might think electronics is a very much a last century development. There was quite a lot of need for quick computation, particularly from accounting businesses, because now you're having mechanized industry. You need to count amount of stuff coming in and amount of stuff going out, as well as your profit. So a large number of mechanical calculating devices were discovered at that time. There was logarithmic there was tables of logarithmic tables comes from those sides, and so on and so forth. What did happen was the security and privacy was a very interesting fascination. At one hand, we lost it to start with. The data was fairly public. Everybody knew what you were doing. But this was again regained as well. There were various societies who were trying to convince that the government should not have all this. So there was quite a lot of losing, regaining, and losing of security and privacy in this era. From sensors point of view, this was also a very fascinating time. A large number of sensors to measure natural phenomena were discovered at this time. There were new instruments. For example, the first picture I have is Torricelli barometer. To measure pressure, we have Fahrenheit's temperature as well as Robert Hooke's microscope. All of these were generally discovered around 16th, 17th century, very similar or very matching the Industrial Revolution. They were not necessarily small, and you still needed a human being to record them, but there was a massive change from how we used to measure temperature, pressure earlier. And we also started learning more about our weather and climatic predictions. We could do that. Industry 2.0 is fairly well known to all of you guys by now. Hopefully, it's the early part of 20th century. We have assembly line working. We have making cars in large numbers. We have more industrial jobs, more specialization for people. People are now factory floor mechanics or wheel designers and so on and so forth. But at the same time, we also have these industrially powerful cities and nations. I mean, Detroit comes up as industrial powerfuls. Birmingham in UK comes up. We have better transport. People start communicating more, transporting more. The postal system already evolved in Industry 1.0, and that has become a bit more mature. Now we get telegram. We can send immediate messages from one place to another. The telegram line between UK and or London and Bombay was one of the first success stories of long distance communication built by Siemens Brothers. So we start getting these kind of things. From privacy and security, we actually had too many wars in this period to know actually anything meaningful as to what happened here. Apologies, my computer decided to freeze at the right time. From sensors point of view, this was also a fairly interesting period. This was a time when we start integrating sensors with electronics. We get large-scale recording, primarily military-led, because remember, we were having two wars between the Industry 2.0, Industry 3.0 evolution. But we had things like radars, that's Freya radar. We had balloon-based weather recording. So we're recording more and more about our data, and the formal recording of our weather predictions pattern started. The last is the weather map of the English Channel on the day the D-Day invasion took place. So a lot of sensory data processing starts happening, still on the pen and paper, but it starts taking place right now. Industry 3.0 is pretty much the world we are living in. If you're not already on the cusp of Industry 4.0, electronics and computers came in. There was a digital connected world happens. New types of workers start evolving. Who is a computer savvy worker? There's rapid changes in technology and society. Our world is becoming smaller again. We have started from a village-based society. We went to disconnected nations, and now the whole world is becoming a village again. We are connected. We are aware about what's happening. And of course, this is improving our quantity as well as quality of life. From a sensors point of view, many things are happening. We are having large number of miniaturized sensors. Last century was a boom time for sensors. We're measuring anything from Earth-based systems to systems in space, and we're measuring all types of things: pressure, temperature, tire pressure, human health. We have machine-based, machines to measure your blood pressure, glucose, and so on and so forth. We have started doing a lot of data transmission and recording, but still not completely automatized. There's a part of automatic operation of this happening, but we're still at the data recording phase. If we can say, we are the early days of what physics used to be 100. We're just observing what's happening in our nature. And with electronics and computing, it's fairly well known. We started from computers which were as big as huge buildings, and now all of us are carrying a mobile phone which is more powerful than the early days computers. We have evolved microelectronic chips, and we have somehow tried to map the three-dimensional world into a two-dimensional world of chips, screens, printers, mobiles. So everything is becoming back to two-dimensional world, primarily limited to the way we manufacture chips. Our microelectronics limits us. What's interesting is the whole paradigm of microelectronics has given us very cheap yet powerful computers. But these computers do not learn. They do not interpret new data or solve unfamiliar problems. AKA, you program them to do something, and they will do that job very, very easily and very, very nicely, but they cannot solve problems which are unforeseen like the human beings as we can do. We can possibly interpret new data and work with this. In recent past, we have started making artificially intelligent systems, and a number of colleagues are working on building algorithms on standard computational hardware, the good old hardware. However, this paradigm is actually not working very well. I mean, these days we are going back to these massive data centers to do our processing. We transmit all the data to cloud, and we hope there's a massive computational power which will be able to compute on this thing. For example, the simple Google Brain project took 16,000 processors and 100 kilowatts of power to identify cat in a YouTube video. My son, who is 5-year-old, can do that job in much lesser amount of power. I guess a slice of toast will be enough for him to identify cats in YouTube videos. So we started from large machines. We went to small machines when it comes to microelectronics. And now we are going back to large machines. We are all just becoming data collection units. And that is an interesting connotation. So Industry 4.0 is on the cusp. Either we are already in, if you believe some of our colleagues, or we are going to be in Industry 4.0 at some point of time. We are having quite a lot of cyber-physical systems, connected people, and hopefully artificial intelligence will play a much bigger role in this paradigm. It's very difficult for me to predict, or for any scientist to predict, what the future holds, but trends are already visible. We are having more connection, more data, more of everything, automation, distribution, hopefully better quality of life. What's not happening is better quality of our senses. Democratic institutions are already under threat in many parts of the world. So that kind of things which we hoped will happen is not necessarily happening. Now, what happened with sensors? Now we have a large number of sensors. We can build, all of us are carrying at least 1 or 2 cameras in our mobile phones, if not many more. We are having automatic running machines, Fitbits, and so on. So we are having a large number of sensors on our body, but also in the wider nature. We have got cameras on the streets. We have got environmental sensors. People are even predict the much better weather forecast we have. So all these things are happening. But what is this doing is that it's also producing a huge amount of data, which means all of this data needs to be moved from these really low-cost sensors to a big processing unit and then stored there for processing. Now, this is in old past, we used to talk about processor memory bottleneck. So in the von Neumann architecture, you have a processor and the memory stores the data as well as your instruction. You need to move data between the memory and processor. And that was a big bottleneck because you can make processors go very fast. Memory was slow, but the connection was even slower. Now we're getting these new bottlenecks, sensor to memory, sensor to processor. So I can make 10 megapixel cameras. How do we transfer all this data to a remote storage and then do the processing there? But at the same time, when you produce a huge amount of data, I mean, all of you will have taken thousands of pictures on your camera phone, which are actually doing nothing. They're sitting there. So we're producing a huge amount of data, which is being left unused or being lost forever because we don't know what to do with it. We can't process them. Question is, can we do better? So in the rest of the talk, I will take two examples from two completely different worlds to showcase how we can do better data processing over this big splurge of data being evolved in Industry 4.0, as well as the Internet of Things era. Before that, let's just take a quick reminder of what a classical sensory system, classical electronic sensory system looks like. We have a sensor. It goes through some sort of signal conditioning. Then most of the sensors will generally produce analog data. We then transfer the data to a digital domain by some form of analog to digital converter. And then we process the data. The processing could be, we display the data, we store the data somewhere, we transmit the data to a central server, and we do further processing. We might infer information out of it, like we could try to figure out if there's a cat in YouTube video. And the problem with this is sensors are cheap. So our electronic components, my ADC is cheap, my camera is cheap, so we can make loads of them. So trend which has evolved is collect as much as data as possible, put as many sensors as you can, and then analyze this data and hope and pray that there is a better computational system to analyze this data. Pray in the sense we have got loads of CCTVs across globe, but just the sheer processing of that CCTV data is so difficult that we have to put a human being to go through the CCTV footage. We don't have an automatic way of doing this thing. So it's a hope and prayer right now. We're collecting data and hoping somebody else will do the processing. We're not doing any data processing while we are collecting this information. So I told you that I will take two examples from two different regimes. Both are close to my heart. Let's take the example of an image sensor, which is a 3 transistor with a diode. So I'll be talking a bit more electronics here. And if you don't follow it, just look at the concept. I mean, image sensor is the basic foundation for a large number of electronic gadgets, be it computers, be they satellite phones, be they toys and mobile phones and so on. They are omnipresent. Some people also may believe that they're omnipotent. We record more information visually than we actually do anything else these days. The image sensors these days are made in the same technology in which we make our microprocessor and memory, and they essentially consist of 3 transistors and a diode. The promise we had when we started moving from the old film-based cameras as well as old CCD-based digital camera was that we will be able to do all of these things. We'll be able to have lower power, lower cost, higher speed, and so on and so forth. But we'll be able to do focal plane processing. That we will not only record an image, we will understand the image while we are recording it. Like what the human eye does. It not only takes the view of a scene, but also tries to start making some inference out of it. At least we know if there's a motion happening, if a tiger is going to come and attack us, that part of thing we can do early. But despite all these promises, the thing which actually made these cameras popular was just one thing. And this is the only thing we look. That's the number of megapixels we have in our camera. We generally do not look at its abilities to do anything else. Megapixel is the driving factor. Which means rather than trying to have information extraction in the cameras, we went through a route of just having more and more pixel. That's what drives the market. We went from 3 megapixel to 5, 10, 20, 100, and God knows where the race was. Maybe we are saturating a bit, but still the biggest driving factor was not extracting the cat in the YouTube video, but just recording too many YouTube videos with much higher resolution. this has led to a number of issues in the sense our images are slightly better quality, but we're also quite requiring much more memory. Fortunately, memory technology has also evolved in parallel, so we are recording, we can store, but transmission bandwidth required is increasing by day by day. And the images are just being recorded and we're not doing anything. So for example, if we have a traffic camera, a 24/7 data generation from a traffic camera will lead to roughly a terabyte of data in a day. So that terabyte of data has to be sent to a server and then done something else with it. At one solution, we have the issue, there are solutions from big data community, how to deal with big data, but it still causes problem with bandwidth in real time. And we're not doing any in-plane processing because in-pixel processing is generally too difficult. And remember, I started talking about computers being 2D world. So we're trying to record light here. So we could make a pixel which had a diode, as you can see here, and loads of circuitry to extract some information out of it. But that means that the size of diode has to shrink to provide place for all of these circuitry, or our camera chip has to be fairly large, none of which is acceptable. If the size of diode is small, then our optical ability will be quite low, will not capture enough light. So such kind of approaches where we put complex processing inside the pixel are not going to fly. People have tried, but the market is not ready for that. So let's take an example where we could move away from this. So the solution, which I believe, is not to think about general purpose imaging solution, but can we have application specific processing on the camera? So right now we make cameras which are fairly typical, can be used from any one application to another application. We're not making application specific cameras. So the way we went in digital world to application specific integrated circuits, maybe we need to go to application specific image sensors. So here is an example of an application specific image sensor. We have three pictures here of the same scene. This is a high dynamic range scene, which means you have got information in low light region as well as information in high light region. Typical cameras fail to record this information. And what we generally end up doing is we take the same image with multiple exposure times and we somehow try to fuse it computationally to look like the fourth image. This is quite a computationally complex process, and it requires doing it on the fly, particularly for video, is very, very challenging. So we have been working on high dynamic range imaging for quite some time, and this was our approach. So we went back and to observe, why does a pixel not record the high dynamic range of information? Typically in a pixel, this is what happens. Light falls on this photodiode and it discharges this node N1. If there's too high light, this node N1 saturates very quickly. It will reach zero at some point of time, and then we lose that information. So rather than having this typical system, we said, okay, can we have just something very simple like a comparator inside the pixel and compare this integration while this integration is happening to a known signal. And this signal we can design in our own way to be any signal. And we stop this integration wherever this comparison flips. So for low light, we just stop it on the top where you can see this VS1 is written. For high light, we stop it at slightly bottom, but we do not allow the pixels to saturate. By doing this, we came up with a new pixel architecture, which just adds one extra transistor. So we don't add a very complex circuit. It adds one extra transistor. And it allows us to do actually any tone mapping operation. So it allows us to not only capture the image, but display the image instantaneously. We do the early processing there itself. And here we are showing the same image captured through different kind of, you can enhance the low light scene, you can enhance the high light scene, or it can enhance the general color contrast and so on and so forth. But this is not a general purpose camera. You do not record all the information. You do lose information there, but you are already tone mapping. You're already compressing the image scene there. And this then significantly reduces the computational overload you have to have in your later processing stage. You don't need to now transmit 3 images. You essentially transmit just 1 image. Here's a further example of event-driven imaging. So if the video works, you might see one of my students doing a somersault in our parks. Now in this scene, the only thing which is important if you're having a security camera is actually a student doing somersault. You don't need to know about all the leaves and sunlight and the road, but the camera is still recording all of that. So rather than doing that, could we do something like this? In this part, we have actually subsampled the whole scene, and we only start increasing the resolution once we identify motion has taken place. So we don't record the whole scene. We could go even further, and rather than just keep on reading random values from a scene, and just look for motion. We don't record the scene, we look for motion here. And when motion happens, that's when we start recording the scene, and only in that part where motion is happening. Now, you might say there might be information in other part of the scene, which we are already losing. We are just not recording the rest of the scene, and that's true. But the question lies, do we record the whole data and then hope later in a forensic way we could identify something happening in other part of the scene, or we just restrict ourselves to recording when something of interest is happening? Other technique which we could try is just not record the whole scene. Again, if you just want to have the information part, for example, here's a classic Lena scene. If we don't even record the whole image and just record part of it, then there are computational techniques, compressed sensing techniques, which can enable you by matrix filling and other things to extract meaningful information or meaningful stuff out of the image. So even if we do not record the whole image, as long as we are only interested in some information, we can reduce the amount of data being recorded and transmitted. I've talked about cameras till now, and I did promise that we will talk about two different imaging modality. Now we'll move to a different imaging modality, which is the mechanical sensors part. Now, traditionally in mechanical sensor world, we have our approach to say, okay, make them as small as possible. And this is inspired by the microelectronics world to have better resolution, more devices per sensor, and so on and so forth. Problems are immeasurably, and I am running out of time, so I'll run quickly. So I'll take an example of a mass spring sensor. This is essentially a sensor which records changes in mass or changes in frequency, and it works by very simple operation of high school physics. If mass changes, the resolution, the response frequency of the system changes. Rather than making one resonator, if we make n number of them and couple them mechanically, we could get a response something like this, wherein if here I've taken a 5 coupled resonance system and there is no electronics attached, these sensors are talking to one another. If the third sensor changes its performance, all these resonant frequencies have changed. Now, rather than recording from each one of these sensors, I'm only recording from one sensor, and I'm allowing the sensors to talk within themselves. This inter-sensor communication or mechanical communication enables me to reduce the amount of data which I'm recording. And we can show the same example with a large number of other sensors wherein they are mechanically coupled with one another. So there's a local mechanical intelligence which we are using in such techniques. Challenges. The bottom line is that sensory integration is the aim of the future. It's integrating sensors with processors, as well as integrating sensors with processing has to be the aim. Images were easy because, well, we know much more about image processing than we know about other things. But even there, processing is still very, very challenging. We still do not know how do we process this huge amount of information. Multimodal sensors are going to be a different beast. If they're not all made in silicon, they're made on different types. How do we integrate them together? How do we make a Star Trek tricorder, which can record a large number of information of different types? The sheer volume of information, sheer volume of materials to sense is quite large. If you're making gas sensors, the number of gases you need to sense could be quite a lot. How do we integrate? How do we make universal sensing solutions? And can these sensors learn? Till now, sensors were fairly passive, fairly neutral beasts. AKA, they did not learn what to do with these approaches. They just recorded the data and transferred it all to the background server. Question is, will they be able to learn? Can we integrate neural networks? Can we integrate some learning system with these sensors so that they can not only acquire the data, but also start doing the early signal processing? That would be the crux of my talk. Early sensor signal processing is vital for reducing the amount of data, particularly Internet of Things era. If we don't do that, the amount of data processing which would be required to do will become very, very large. You could start doing sensor processing systems wherein we could have things like we put more and more signal conditioning into the sensors, or we start making sensors talk to one another. This could be in form of mechanical sensors, as I talked about, or it could be in terms of having neural networks attached to the sensors next to one another. And this is the approach where sensors designers, rather than making the best possible sensor, best reasonable sensor to do, we need to start thinking about how do we integrate different kind of sensor modality together, and what do we go from here. With that, thank you very much. I will stop now, and if there are any questions, I will take that. And if there are no questions, I will go back and discuss about mechanical sensors and how do we couple mechanical sensors. Thank you very much.
Thank you, sir, for that informative session, starting from the evolution of sensors and discussing the recent advancements and challenges in deployment of sensors in today's scenario. Moving on to the question and answer session. If the participants, any of the participants have any questions, you can post it on the Q&A.
While we wait for the question, I will quickly remind you that I did not run through, I ran a bit quickly on the electromechanical sensors. And the rationale was that I thought I was running a bit faster on time. But here, these sensors are meant for gas sensing operations. For example, we could have 5 different gases being measured on each one of these sensory elements, and they could be measuring n number of 5 in this case, but we could make n number of sensors which are coupled with one another. And by measuring, doing this modality, we could, in principle, or in practice as well, have the ability to measure more than one type of sensory systems in a solution. So we could, in future, integrate things in the frequency domain or in other domain to have be able to measure multiple sensors. Though there is a fundamental limit. In our electronics world, we are limited with the noise profile of these sensory systems, as well as how we have a finite frequency to measure this. So we need to think of solutions of having local intelligence. Could it be mechanical intelligence? Could it be neural networks in form of mechanical world? And that is very vital for us to progress here. And if there are no questions, then I will leave you in peace to have your tea.
Any questions? I think there are no questions from the audience side. Thank you, sir. Thank you for that informative session.
Good. Have a good day, all of you. Bye.
Now, we move on to the session, Edge Intelligence, Engineering the New Fabric of IoT, Edge and Cloud. Will be delivered by Dr. Shahram Dasdar. Dr. Shahram Dasdar is a professor of computer science with focus on Internet technologies, heading the Distributed Systems Group at the Vienna University of Technology. From 2004 to 10, he was honorary professor of information systems at the Department of Computing Science at the University of Groningen, the Netherlands. He is a member of the Academia Europea, the Academy of Europe Informatics section since 2013, and an IEEE senior member. He is recipient of the ACM Distinguished Scientist Award, the IBM Faculty Award, the IEEE TCS/VC Outstanding Leadership Award, the IEEE TCSC Award for Excellence in Scalable Computing. He serves as the editor-in-chief and associate editor of several reputed international journals. He has held top positions in both academia and industry and is currently the charter member of the Association of Information Systems, member of the IEEE Computer Society, ACM, GI, and Austrian Computer Society. On behalf of KUTSIT, I invite Dr. Shahram Dasdar to deliver his talk.
Thank you very much. Just checking, can you hear me well and see my slides?
Yes, sir, you can proceed.
Okay, wonderful. So thank you for joining this session. In this talk, I'm gonna talk about what I call edge intelligence. And this is essentially the area where we look into creating a new fabric of distributed systems technologies. And in particular, I'm gonna discuss Internet of Things, edge computing and cloud computing, and how they are related to the question of AI and intelligence in general. So the first assumption or observation rather is that we are living in an age of smart evolution. So what I mean here is that we have three building blocks of systems which are increasingly being weaved together into what I call elastic systems. What elasticity is, I will discuss as we move on. And these three building blocks are people, are software services, and are the things in the sense of the Internet of Things. And what is kind of novel in the world of information systems or computer science research is that the people are becoming first-class entities in these systems. They are not just only outsiders interacting with the system, they are becoming integral part of the system. And the Internet of Things, in the sense of the objects, are also processing machines, and that was traditionally outside the scope of computer science, was more of concern in electrical engineering, for example. And this is kind of a new situation. We have new breeds of systems where we have like smart home systems, e-health networks, governmental networks, transportation networks with autonomous vehicles, even energy networks. And all of these types of systems are having these three components to certain degrees, which vary over the different class of the systems. So the question for us designing these systems and these infrastructures becomes then, how do we delegate certain aspects of the work that needs to be done between these three building blocks? And it is non-trivial to actually do that. We can say then that all of these things are actually connected with each other, similar to this picture, right? So whenever you move one aspect of it, the other aspect moves as well. So whenever we think of a system such as this, I think natural systems are very helpful to understand the principles. And in this case, I would like to draw your attention to natural ecosystems like the one represented here, the marine ecosystem. Here you can see the sun, the birds, the water, the rocks, the animals inside the water, etc. And all of them are building the marine ecosystem, and they are in relationship to each other, represented by these yellow arrows. And we can say then that this is a complex system. It has network dependencies, and it has then also adaptive intrinsic behavior. And these yellow arrows are quite fascinating, basically, because they say something about the relationship, which is kind of hidden when you look at the ecosystem itself. And in nature, there are four important mechanisms. The first one is robustness and resilience, which allows us or allows nature to achieve stability even in the presence of disruption. The second one is that we can have measures of health. So in other words, when we look at such a system, we can measure its diversity, the population trends, and other key indicators, and then saying something about how healthy is that ecosystem. The third is it has built-in coherence. So this means it has a certain degree of a purpose, a direction. It knows how to evolve over time. And fourth, it is to a certain degree entropy resistant. This means that basically it kind of defies the natural tendency to entropy, to disorder, if it is not shaken up too much. And my fundamental assumption in this talk is that the systems that we have seen in the nature and still see in the nature are actually very similar to the ecosystems for distributed systems, where we have compute, resource power, networking, what have you. And we have to think about how do we actually bring all of these together in a way in which they resemble the mechanisms of natural ecosystems. Because currently we do not. We have isolated systems. I will talk to that in a minute. A good example where all of this is being tied together is a smart city. In smart cities, we have all sorts of things. We have sensors for fire, air, traffic, video surveillance, etc. We were talking about this in the previous presentation. We have different software systems for picking up these data, doing disaster management, traffic control, detecting persons, automated parking, watering services, garbage collection, etc. And we have us, the people running around in the city, and actually also leaving data, right? So what we have learned in the last decade or so is that all of these building blocks should be provided as a service. So everything is provided as a service. And by means of providing as a service, we are able to actually link all of these different aspects together. So that was basically the foundational achievement in the last 15 years, which led then to the evolvement of cloud computing, which is so immensely popular. It is so popular that everybody is using it, right? So we can now begin to look into more details here. So there is one observation. It is that we are seeing new families of applications arising, which require some real-time location-based access to that data from the environment at different levels of fidelity. So not every application requires the same granularity, fidelity of the data. This is a very important observation. The second one is that appropriate compute and storage resources in close proximity to the data producers and consumers are required increasingly. And that is, for example, for application types such as gaming or different scenarios in autonomous driving, where you need extremely low latency of the data. And these classes of application, these new families of applications, are increasingly gaining momentum. One example which basically I think is very important for us to observe is what I call here dynamic analytics. And what I mean is the following. Consider now for a moment, look into the world of managing the pandemic. When we are managing the pandemic, what you observe is that we have a set of different isolated subsystems which we are looking at. So we have the world of simulation, where some simulation scientists make some assumptions, and based on those assumptions, actually we derive some policies. Then we have systems which look at patterns of actual movement of the people in a particular city or across different nations, etc. So what we can say is that we have different vertically isolated subsystems which we are not able to tie together. And by our lack of the ability of bringing those systems together in real time, we basically miss the opportunity of managing our affairs in the society, right? Because this is actually a reflection of my initial argument. We have the people, we have the software, and we have the things having to work together in harmony in order to actually be able to provide some analytics. If you look at this picture now, you can see that we are having systems in horizontal domains and in vertical domains, and they are pretty much isolated. We are not able to pull these types of systems together in real time in order to make meaningful, to provide a meaningful basis for decision making for our affairs in society. And this is increasingly becoming a problem for our survival, because we have to integrate these systems and in order to make right decisions. Similarly to the human body itself, everything is connected, right? So we cannot just look at isolated systems. Maybe we can look at them, and we do that when there are hard cases where it's a question of survival, emergency, etc., emergency medicine. However, if you want to create a healthy organism, it is well known that you have to look at the whole system. It's kind of a holistic problem. So I want to point you to a paper. I don't have time for this in detail, but here we actually challenge the divide and conquer mentality, which actually led to the current state of affairs that we have in our systems world, where all of the systems are kind of separated in isolation, and then we create interfaces in order to let them communicate with each other. However, if you look at natural systems, and even our own autonomous nervous system, the system design is actually different. And we argue that actually we need to have a different design, but there's not enough time here. So I just wanted to put you to this reference here. So nowadays, there are different perspectives on these infrastructures that we have talked about before, right? So we have the cloud-centric perspective, which looks at the cloud as the center of the infrastructure world. And we have different edge computers and different things evolving around this cloud universe. The internet-centric perspective, on the other hand, looks at the internet as the basic topology and infrastructure where the things, the clouds, the edges, etc., connect with each other via the internet. And both of these different perspectives are actually prevailing today. However, as we observe, the cloud-centric perspective is actually the standard today. That assumes that all of the sensors, all of the data that the people are creating with their smartphones and their smart watches, etc., in the cars, all of that data is being transported to the cloud. The magic sauce is there, the algorithms are there, everything is processed there, and then the data is coming back and something is being done, actioned on that. The other way is to look at it from the internet-centric perspective, where the assumption is completely different. And the assumption is that you do have autonomy at the edges of the network. So in other words, my camera might have more intelligence, might have the idea that it can process and make some decisions, have some AI on the camera itself to make the decision to send the data further to the cloud or not, to create models for further processing or not, to do the processing possibly even itself or not. And then the cloud is also connected to that if needed. So then we can basically see that actually what is there from the infrastructure perspective, we have an IoT edge fog cloud continuum, as I call it here. So on the left-hand side, you basically see low reliability devices, which are highly volatile, they are very mobile, they have a small form factor, they have energy battery constraints. Typically, they are controlled by us, by the users. Some of them are possibly controlled by a service provider. So this is the world of the edges, the IoT and the edges. When we move to the right, we see a typical edge compute infrastructure, which is typically edge devices, which are computers, little servers, if you like. They have low latency. They are connected via the mobile network. They are general purpose computers. They have standard architectures. Typically, they are possibly telco operated, not necessarily, but possibly. And if you tie them together even further to the right, we have the fog computing domain, which is typically 5G base station type of equipment operated by the telcos or possibly by IT companies in the future. We will see how that evolves, where and kind of consolidating that data coming in. And on the right-hand side, we see the typical cloud domain, which is well understood nowadays, which has, under quotes, unlimited compute and storage resources. It has high availability, low cost, etc. So the question for us then, as the designers of these systems, becomes how do we actually get rid of an isolated, vertically isolated worldview where I, as a designer of a system, has to basically write the application for one particular topology of the system. This is a foundational problem because the applications themselves, based on these different requirements that we are facing, have to be distributed across this compute continuum, have to work in different ways of this infrastructure. That's why I was talking about a fabric of distributed systems infrastructure. So the question is, how is it actually possible that I create applications which are spread across this big spectrum of types? If you zoom into this, you can see basically that it becomes a problem of offloading, under quotes, horizontally or vertically the application parts, the microservices, if you will. So which resource in this overall fabric of computing is actually taking care of my application? Which part is actually hosting the services that are doing the compute, the storage, etc. Right? And my argument in this talk is that in the future, we have to build in the mechanisms for this decision making into the infrastructure itself. The infrastructure is becoming an intelligent infrastructure, which makes the decisions where to actually operate these services, where to provide them, where to host them, etc. And that has tremendous implications for business, for managing, for governing the whole infrastructure, as well as the applications. So if you look at this compute continuum, an example, you can go from the left-hand side from servers to data centers, to the right-hand side to microclouds, where you have a bunch of Raspberry Pis being put together in microclouds, right? So the range is tremendously interesting. Down to specialized compute platforms, where you have things like the Google Edge TPU, NVIDIA Jetson cards, or Microsoft or Huawei different hardware devices being specialized for AI, for different types of processing, which build then on top of this infrastructure. So the question becomes, do we have to write our software for each of these different devices, or is it possible to create the software which is basically being operated and hosted on these different devices? Because there is a tremendous range in the cities, right? From little computers to array of things like we see on the right-hand side here, from air quality sensors, different weather environment sensors, to bigger compute devices like this Huawei Polestar. So there is a huge range of these things. My argument here would be to see this whole infrastructure like a zoo, basically, to basically understand that we are living in a world of software intensive systems, and that as software is better able to actually manage the conflicting system factors and the different requirements to create a trade-off, we have to look into the software intensive part more prominently. So this means that we look into latency as a first-class citizen, where we see the inherent traditional division of the cloud IoT, which is affecting different time aspects and performance aspects. We see computation as an edge resource, because the edge actually, if you are able to provide resources of processing, storage, etc., to the edge or from the edge, you are actually increasing safety and security, and at the same time also privacy, as we see in the last point. So privacy, different parts of software configuration and evolution of software is much improved when you shift the focus to the edge, where the data is being created, it is closer, you have lower latency, higher security, better privacy, etc. And then the question becomes, which characteristics of these edge computing systems should be actually abstracted as first-class citizens into the underpinning model? Now, this is a fundamental question. This is not something that we can basically fix in a paper or so. This is a research agenda for a whole community looking into this. And I would like to propose two particular mechanisms for looking into this. The first is, if you think about this, one hypothesis would be to look into the areas of proximity, context, capability, and energy. That actually makes the decision where to put the compute, the resource, etc. In this talk, I would like to focus on one mechanism or two mechanisms, basically, which we have developed over the last decade, which I call elastic diffusion. So elasticity is a principle in physics and material science, which says something about the property of returning to an initial state of a material following some deformation. So you put some force on a material, it deforms, it stretches maybe, and when you get away with the force, it shrinks or goes back to its initial form. Now, this elasticity is a very interesting property for building resilience in systems, because if you have rigidity, it is actually not, it would break, right? So this elasticity principle brings with it the resilience that we are aiming at, similar to what we have in nature. And if you observe, in the past, we have built systems which are essentially scalable. Scalability means that we build systems for the worst case. So the maximum number of users, the maximum resources that we provide for the worst case under quotes, and that is it. However, elasticity has a slightly different semantics in my view. It basically talks about a trade-off model in a three-dimensional space. Because we can add and remove resources, so we have resource elasticity, but there are two other dimensions as well. We have quality elasticity, which looks into the quality of the data coming into the application at that given point in time and leaving that part of the service at any point in time. And we have cost elasticity as well. So in other words, when we design applications, we are designing those applications within this trade-off model of this three-dimensional space. So in other words, we are saying, I want to use these resources only if they provide that quality of the data as an input and they don't cost more than X amount of euro or dollar or whatever. So in other words, we are operating in what I call here an elasticity space. And we would like to be able to specify that elasticity space for any application on the infrastructure. So this means that we have created a language, and with this language, I can specify the requirements that I would like my application to have at any point in time on different levels of abstraction. So this language is called Sybil. And as you can see here, we can attach these requirements to the cloud service level for application services which are provided on the cloud and I don't have access to the implementation, to the service unit level, to even to the code region level. And then my dashboard basically shows me which parts of my application are not fulfilling the defined constraints, and then tries in the infrastructure itself to provide remedies for that. So for example, shifting the application, the service, from one virtual machine to another one, represented by these green puzzle pieces, or by deploying it on a different server. So that is the idea of having a dynamic fabric where you are moving around these different parts of your service infrastructure. So in other words, we can say that an application is always in this three-dimensional space represented by this triangle, having quality, cost, and resources specified. And with this elasticity model, I can basically say then, is my application operating inside this elasticity space? In other words, inside these orange lines over time. If not, I would be losing money. And the second is the elasticity pathway function. It basically characterizes the elasticity behavior from a general or a particular point of view. So this is the pathway over time, how my application is actually evolving as it moves across the infrastructure. So this is something foundational because it says something about how the application is operating in this three-dimensional space. The second aspect is what I call elastic diffusion, also known as osmotic computing. So osmosis is a principle in chemistry, and it represents a seamless diffusion of molecules from higher to a lower concentration solution, right? Represented by this. And the idea is basically very simple. The idea is that what you can see on the right-hand side in the bottom in this figure is that when I write software services, actually these software services represented by these little triangles and bubbles, they are able to be hosted on edge computing devices of different sorts up to cloud computing devices of different sorts, providing the specified levels, quality of service, etc., as we have specified them. So here, the dynamic aspect is the important point of attention. Now, these principles in place, we can move towards building an infrastructure which might be called edge intelligence. So this computational fabric basically has to be flexible and modular as an infrastructure, and it has to provide intelligent operations in order to scale to that infrastructure. And it has to have an automated AI lifecycle management down to the edge, meaning that the pre-processing, the training, the model creation, the model compression, what have you, has to be distributed over the whole stack of the compute continuum. So this fabric for edge intelligence then basically has three important aspects. The first one is the sensor data as a service. So there are a large number of dynamic and mobile nature of publishers and subscribers of this sensor data, but currently the things of these messaging services are centralized, like the Amazon Web Services or the Microsoft Azure IoT Hub. So we have to move to a distributed and decentralized sensing infrastructure. Secondly, increasingly what we see is edge computer networks with modular AI capabilities. This is what we require to build into the fabric as well. So as I was talking about these AI specified cards that are paired with general purpose computers. And thirdly, all of this needs to be orchestrated, coordinated for decentralized and distributed infrastructure. So the focus also has to go to the orchestration of all of this. Now, digging even deeper, we can say then that we have to have federated learning in these distributed systems where we can have training on that data directly on these remote devices without actually revealing the data themselves, sending the outcome of local trainings to some servers on different levels of abstractions, can be edge devices, fog devices, or cloud devices. And these different servers then aggregate these updates into some global model, and then make these models available to the necessary devices, right? So as a principle, we have to apply federated learning to these distributed systems. And that is useful for many types of applications, for mobile devices like face detection, voice recognition, etc., where the users don't wish to reveal their messages, photos, and videos, but still we would like to gain the benefits from this model building. Or for organizations such as a hospital, where you want to have the data, but you don't want to expose the individual data, like in the COVID case, right? Or for bigger entities, for environment, for transportation, and other types of applications. So there are plenty of research challenges which we face in this aspect, which is a call for us, all of us. So device recruitment strategies to make decisions, which subsets of these devices actually do we use? It's highly volatile, so these devices can disappear or join at any time. We have asynchrony, so these algorithms face the challenges when end devices do not submit their data in a timely manner. So this leads also to some bias. We have a non-independent and identically distributed data. We have heterogeneity in the volume of the training data per device. We have to prevent privacy leaks, and we have to think about incentives, how to stop misbehaving. So like, why waste battery when I can let others do all the work? So for this, we came up with a research roadmap, which we published recently, which looks into the end user as the quality of experience that he or she experiences on 5 different criteria, such as performance, cost, privacy, efficiency, and reliability, and then translated those into 2 areas of AI, which I don't want to go into the detail in this talk because otherwise it gets too long. That's why I hint you at this paper, where we distinguish between AI for the edge and AI on the edge. And in that paper, all of these aspects of research questions are discussed in detail and provided a research roadmap for these different areas, how to build that computational AI fabric here. So to conclude my talk, we can say that the first takeaway message is that we need to leverage the whole compute continuum from the IoT to the edge to the fog and to the cloud. So, and we look at this whole continuum and not just one isolated thing in order to create the distributed infrastructure. Secondly, we have to learn to differentiate between AI for the edge and AI on the edge. They have a lot of many research challenges ahead of us. And thirdly, we need to build in this edge intelligence, the whole fabric, and have an understanding that what we are talking about is not some algorithm which is deployed here or there, but it is an infrastructure which is a distributed systems ecosystem. And as such, we have to deal with it in an infrastructure way. And with that, I thank you very much for your attention.
Thank you, sir. Now we can move on to the question and answer session. If anyone has questions, please post to the Q&A.
So there is
one question
one
is there. Sir, can I read the question?
Yes, please.
What is the difference between edge analytics and edge intelligence?
Right. So the way I see it is that edge intelligence is talking about the larger picture of what I was talking about. And edge analytics basically discusses the question, deals with the research question associated to providing analytics functions on the edge device itself or for the edge devices. So that's kind of a granularity question. One is on the higher level of abstraction, looking at the whole question of different intelligence mechanisms, and analytics is one particular.
The next question is, you have mentioned that in edge intelligence ecosystem, the edge devices can function on their own way from cloud. The question is that, will this not increase the cost of such devices as they should have faster microprocessors and storage?
Yes, indeed. So what we are observing is that this is now kind of splitting up the business of all of this, right? So this means that you can have edge devices which are under your control. You have the processing power, and not everything is delegated to a subscription model to the cloud. So this means that, of course, the cost of processing on the edge devices, which is owned by you, belongs to you, right? The energy consumption, etc. However, it comes with other benefits, such as I was also speaking about, increasing the security, the privacy, and the latency aspects in case you should need them, right? So that it is a trade-off, and I think that we need to better understand this trade-off. Hope that answers. The third question, the less than 5 milliseconds and 10 milliseconds, are we there? Yes, indeed. So we are there if we take into consideration these edge devices and possibly also 5G in concert with that. So we are there, but of course not everywhere, right? Because make no mistake, still the majority of the systems are not operating on this whole continuum as I was talking about. So the majority of the systems are systems where you have them executed somewhere on a server, and they send massive amounts of data to the cloud, and that's also quite costly as well. And in those systems, you don't have that latency that you are asking for.
Thank you, sir, for answering the questions. It was a very informative session, and it was very interesting to listen you explaining the vertical versus horizontal edge, fog, and cloud architectures, the software-intensive edge systems, especially the federated learning in distributed systems. And you have pointed out the research roadmap and current research challenges, which will be very much useful for the young researchers. Thank you very much, sir.
Thank you very much. Wish you a great day.
Thank you, sir.
Thank you.
Moving on to the next session. Our next session is handled by Professor Vincenzo Fiori on the topic Artificial Intelligence for Industrial and Environment Applications. Professor Vincenzo Fiori is a full professor in computer engineering at the University of Milan, Italy since 2000. He has been associate professor at Polytechnic of Milan, Italy, and visiting professor at the University of Texas at Austin, USA, and visiting researcher at George Mason University, USA. His main research interests are artificial intelligence, computational intelligence, intelligent systems, machine learning, pattern analysis and recognition, signal and image processing, biometrics, intelligent measurement systems, industrial applications, digital processing architectures, fault tolerance, cloud computing infrastructures, and Internet of Things. Original results have been published in more than 400 papers in international journals, proceedings of international conferences, books, and book chapters. He is a fellow of the IEEE, distinguished scientist of ACM, and senior member of INNS. He has served as the editor-in-chief and associate editor of several reputed international journals. He received the IEEE Instrumentation and Measurement Society Technical Award in 2002 and the IEEE TAP Hall of Honor in 2019. On behalf of Kudsit, we welcome you, sir, to deliver the talk.
Thank you for the nice introduction. Ladies and gentlemen, good afternoon. Namaste. It is really a great pleasure and an honor for me to be here with you this afternoon and talk about the use of artificial intelligence in a broad variety of applications in the industry and the environment. In particular, we are going to see which are these typical applications, which is the goal of this application, and how we can use artificial intelligence to increase the capability of the designers in achieving better accuracy, better performances for the systems in the various aspects of the computation that is typically needed. In industrial applications, basically we have two different aspects that are essential. The first one is the management of the manufacturing process itself, the control of the process, the analysis of how the process is working actually, and making sure that the behavior is the desired one. This will ensure a quality of the output of the process. It will ensure a quality of the products that are created by using this manufacturing process. The second aspect, which is more and more essential in the modern manufacturing systems, is the quality. In the past, we were used to focus on producing a huge amount of items, a huge amount of products. But more and more, the market is looking also for quality of the products. So what we are increasingly interested now is not only to produce a huge amount of products for the big markets, but also to produce quality products so that we can ensure to satisfy the needs and the preferences of many customers. And this will also allow to have a different cost for this item, a different price for the items that we produce, so that if the quality is a little bit lower, we can sell these items at a lower price. But for the higher quality items, we can increase the cost, the price, since the customers will be anyway willing to buy items which have been certified of high quality. And this is why it's essential in the manufacturing processes to embed the capability of certifying the quality, and not certifying it as we were using in the past on a statistical basis, taking a batch of products, picking some of the items that we produced and check the quality of these items, assuming that these items are actually representative of the quality of all the other items in the batch. What we wanted to do nowadays is to be able to certify individually the quality of each item. This is the reason for which an automatic system becomes essential in order to achieve this goal. On the other side, the environmental applications are typically consisting in monitoring the environment to look at what is happening in the environment for a broad variety of purposes, to monitor pollution, to control the pollution, or to monitor what is happening in the natural deforestation or climate changes or other various aspects that are important for the life of people, for the well-being of the planet. Many of the tasks that are needed are very boring and repetitive. And in some cases are also dangerous since they may need to be carried out in areas in which the hazard is high. The use of computerized systems actually helps in addressing both of these aspects. The automatic systems are accurate, they are non-invasive in many cases, they produce a standardized quality certification, homogeneous during the entire production, and they do not become tired. So they ensure the same quality of the observations. Basically, what we are doing is to take the signals during the manufacturing process. We extract the relevant features which are related to the behavior of the manufacturing process, to the quality of the products, or to what is happening in the environment. And using this list of features, we analyze the status of the process, the quality of the process. These techniques are important in a broad varieties of phases during the monitoring and control of the processes. In particular, we need to look to the sensors and the measurement system. We need to look to signal image processing, to look for the sensor data analysis and fusion, and classification, clustering, and control, since all these aspects contribute to create the manufacturing control processes system, the system for quality assurance, and the monitoring systems for the environment. The traditional techniques, the algorithmic basic techniques or statistical basic techniques have a pretty good complexity in general, but the problem is that it's not always easy to define them. If we base them on physical models, we need to know exactly the physical model. We require the model of the processes that we are observing, of the phenomena we are observing, and this is not always easy to get. On the other side, also from a statistical point of view, we may need examples of the behavior, but we need to understand a priori which is exactly the type of statistical model which is better capturing the behavior of our system. And as a consequence, they may have limits. Artificial intelligence provide additional tools to the designers to address the modeling and control system in a different way with some more flexibility if enough information is provided to configure them. Neural networks, for example, are mimicking the behavior of the brain, but they can be configured to learn from the data without the desired behavior, without having the need a priori to define the specific type of model. The fuzzy system allows to capture some characteristics which are expressed in linguistic terms and not in exact numbers. Evolutionary computing are mimicking the natural evolution of the species in order to perform optimization. And then there are also machine learning techniques and many other knowledge extraction methods, knowledge representation method, which can be effective to create an adaptive system, an intelligent system capable to adjust its behavior to the actual status of the environment. What I would like to point out is that in many cases, the use of a single computational paradigm for the entire problem may not be the best approach, since each computational paradigm may be very effective in some cases and not so much in others. So the use of a composite systems in which we define the entire system that we wanted to implement, and then we partition it in pieces according to the specific subfunctions that we wanted to implement, and then we choose the specific computational paradigm which is more suited for that specific part, will allow the designer to have more degrees of freedom. And on the other side, it will allow the designer to get a higher accuracy and a better performance for our system. In particular, this approach is very effective in the various phases that we need to address in creating the monitoring and control system for industry and environment, from the signal acquisition to the control and the optimization. For signal and image acquisition, we have several conventional techniques which have been shown as very effective, but also the artificial intelligence techniques provide a good additional set of tools for self-calibration, for linearization, and for error detection, for fault detection. Signal preprocessing, signal and image preprocessing are important since when we collect the data from the sensors, they contain noise. They contain some errors due to the nature of the sensors. And as a consequence, if we use the data raw as they come from the sensors, we need in the subsequent phases to learn not only the desired behavior, but also to learn the presence of the noise and take this into account when we define the desired outcome of our tool. Using signal preprocessing, image preprocessing, we can actually remove as much as possible the presence of the noise, and as a consequence have better quality signals so that the subsequent phases will be much simpler to design. The second aspect, which is very important, is that from a signal, we may not be interested in all characteristics, all data containing in the signal, but we may be interested in some specific aspects. For example, in a signal, we may be interested in the maximum peaks of the signal, or in the slope of the signal, since these are characteristics which are related to some specific physical behavior in our system. As a consequence, we do want to extract these features, this information from the data, since these features are relevant to understand the status, the behavior, the quality of our system. Neural and fuzzy techniques have been shown very effective both for signal and image preprocessing, for noise removal, as well as for identifying the values of the features in which we are interested in. But how many features we needed to extract from the data that we are collecting? Since if we collect a few features, of course the complexity is low, but also the quality is low. The accuracy is low. If we extract many features, not necessarily we increase the accuracy of the knowledge that we have. If we have two features which are related by a physical law, when we get one of them, automatically we get the other. So we are not increasing the knowledge of what we are observing. In order to identify the most appropriate set of features, there are several techniques, both from the traditional algorithmic point of view, statistical point of view, by using principal component analysis and many others, as well as from the point of view of artificial intelligence, based on neural networks and fuzzy systems especially. Another important aspect is that in many cases, in order to have a better understanding of the status of what we are observing, we may need to merge together several information coming from different sensors. We need to perform data fusion. And neural networks have been shown very effective in this perspective, as well as add some specific techniques based on fuzzy systems. We may need also to create some virtual sensors, sensors which are not attached to physical devices, but are an abstract processing of data related by physical laws to the quantity in which we are interested in. Just as a quick example, if I am interested in the humidity of the soil to support agriculture, I can distribute in the ground several sensors, humidity sensors, but this may have some difficulties in managing the connection. They can be destroyed by animals or by the regular work in the field. What I can do is actually to use a satellite, a drone, an airplane, a balloon, to collect the amount of light which is reflected from the soil in some specific bandwidth related to water. So the amount of energy which is coming from the sun at that specific time in this bandwidth with respect to the amount which is reflected from the soils allow us to create a virtual sensor which measure the quantity of humidity in the soil itself. Classification, clustering, pattern recognition are essential in a broad variety of the applications related to manufacturing, quality control, and environment. With the value of the features which are characterizing the status of what we are observing, we can implement a classifier or a clustering technique or detect the patterns according to the specific application in which we are interested in. The last step for obtaining the desired behavior of the system we are observing is the control. We need to impose some specific value to the actuators through the actuators in the system in order to ensure that the system behave as we desire. Neural and fuzzy techniques have been shown very, very effective in this purpose. There are many examples in which these techniques have been able to provide better quality in the control systems, more flexibility, and the ability of learning from the examples. In other cases, the traditional techniques are effective, but if we do not have sufficient information to design the control system by using the traditional control techniques, we can try to extract the desired behavior, from example, by using neural networks or by expressing some non-crisp quantities by using the fuzzy-based control. The last step, the last area in which artificial intelligence can be useful is in optimizing our system. If we have many parameters that need to be optimized, the traditional approaches, algorithmic approaches, heuristic approaches provided by the operating research may not be sufficiently effective in the case we have many local minima and or maxima, and as a consequence, they tend to remain stuck in an area. Evolutionary computing allows to jump more freely here and there in the domain in which the system is defined, and as a consequence, be able to find better solutions. Basically, the contribution of this talk is to point out that the monitoring and control is very important for advanced manufacturing processes to ensure high quality products, and as a consequence to allow the economy to maintain or improve the economical leading role, to increase the revenues for higher quality products. On the other side, also environmental applications are more and more important in order to ensure a livable environment for us, a sustainable environment, to reduce as much as possible the pollution, and to make sure that the environment is safe for people. And artificial intelligence has been shown effective to provide many additional opportunities for creating adaptable, evolvable systems with some intelligence inside, which is able to analyze the data and create the models and create the control directly from the experience. Thank you. If you have any question, I will be very happy to answer.
Thank you, sir. There is one question from the audience side. Virtual sensors or virtual measurements?
Well, the measurements are real, are physical measurements that we are doing, but what we are creating is a sensor which is not the one touching directly the physical quantity that we wanted to measure, as in the example of the humidity I pointed out before.
Any more questions from the audience side? Have any questions? Please post it on the Q&A. There is one more question. How to find good data?
Well, data coming from sensors are data. There is not a good or bad data. It depends on what you mean with good data. If you can elaborate on that, I will be happy to answer more accurately.
So there is one more question. For AI, data is everything.
Well, if you have, yes, I've seen it. I have the question and answer in front of me. Well, for artificial intelligence, the techniques of artificial intelligence are based on the analysis of data. So if you wanted to configure a model in artificial intelligence to solve a problem, you need to have the data about the specific problem you want to address, and you need to understand what you want to do, which is the goal of using artificial intelligence. Also in this case, if you mean that data are essential for artificial intelligence, I would like to point out that data are essential for any technique that is based on the analysis of data, on every model that needed to be configured by using the data. Also, if you are considering statistical based approaches to solve a problem, you need to perform a statistical analysis. You need the data also for this type of approaches, since otherwise you cannot create the statistical model.
Thank you, sir. Is there any more questions? Any more questions from the audience side? We think there are no more questions. It was indeed a great and interactive session, sir. Thank you for discussing how AI can be utilized in monitoring and quality control systems, and for discussing the additional opportunities for adaptable and evolvable systems. Thank you. Thank you, sir.
Thank you. Have a good afternoon. Namaste.
Thank you, sir. Thank you, sir. Now moving on to the next session. The next session is handled by Dr. Saugata Mukherjee on the topic Analytics and Industry 4.0. Dr. Saugata Mukherjee is a senior researcher and senior manager of the Telecom Research and Innovation Center in IBM Research India. Before joining IBM, he held research and software architect positions in companies in Silicon Valley, California, including NEC USA, Intomi, and BEA Systems. His research interests include middleware technologies and its applications to telecom, information retrieval, and text mining. On behalf of Kudsit, we welcome you, sir.
Hello, everyone. Can you hear me?
Yes, sir, it's audible.
Okay. Yeah, good afternoon, everyone. So I will talk on the topic of Industry 4.0 and some of the enabling technologies for that, like IoT, analytics, and cloud. So we are in the cusp of this Industry 4.0. As you know, the history of our civilization, we have moved from Industry 1.0, which was introduction of mechanical production machines powered by water and steam, to Industry 2.0. And then we had the industrial revolution of Industry 3.0, which was the use of electronics and IT. And finally, Industrial Revolution 4.0, which is based on cyber physical systems. So what a cyber physical system? A cyber physical system is a system of collaborating computational elements controlling physical entities. And CPSs are physical and engineered systems whose operations are monitored, coordinated, controlled, and integrated by a computing and communication core. So they are the grasp of the Industry 4.0 revolution. And so what it allows you to do that we can have integrated cyber physical system, which will have continuous monitoring, structural health monitoring, remote diagnostic and remote control, and which will lead to communicating self-control systems in multiple places. So for example, smart factory, smart cities, smart grid, smart logistics, smart products, and so on. So what are the design principles of Industry 4.0? So these include IoT and IOP, so which was one of the core elements of the cyber physical system. Information transparency, then decentralized decisions, where the ability of cyber physical system to make decisions on their own and to perform their task as autonomous as possible. So instead of a central authority making decisions, each of these IoT devices can make certain decisions of their own and they can act together. And finally, technical assistance, the ability of cyber physical systems to physically support humans by conducting a range of tasks. So as we talked about, so the key element of a cyber physical system, which is the backbone of Industry 4.0, is Internet of Things. So we are all aware now of Internet of Things, which are communicating objects based on internet technologies. It can detect identification and location of physical objects, and these of all of these objects are smart by themselves. They can make decisions of their own and can communicate with other devices that are nearby. So IoTs will also lead to Internet of Services, which is a new way of providing internet-based services. So this can be depending on the type of demand. You can have different types of services, and you can have different IoT devices providing the logistics and the smartness below. And all of this will lead to Internet of Data. Each of these IoT devices will provide a lot of data, so you need big data technologies so that you can understand and make full use of the IoT devices. And this is a fundamental prerequisite of providing holistic security and safety culture and enabling a trusted environment. Okay. So obviously, IoT is driving digital disruption of the physical world, and IoT cannot work on its own. It is based on many other enabling technologies, which we are focusing in this talk. So the IoT devices, of course, will lead to a lot of data, and therefore you need AI and analytics so that you can make a understanding of the knowledge that these devices are providing. You need cloud computing technologies because the way this IoT devices they act on their own, but there needs to be part of a overall ecosystem which can be provided by a cloud computing platform. These devices need to have pervasive connectivity so that they can connect with each other and they communicate among each other. And of course, the key to the IoT systems are embedded sensors. And based on all these technologies, they are transforming every part of the business. They're boosting operational performance and lowering cost, driving engagement and customer experience, creating new products and business models, and of course, advancing the environmental leadership. Okay. So with IoT, companies are becoming more competitive with new ways to drive better business engagement. So companies that are embedding IoT and the related technologies, they are becoming the leaders. And if you don't embrace these technologies, then you are falling behind. So for example, can I reduce the maintenance cost by doing conditional repairs instead of time-based maintenance? So how can I save energy? I need to reduce element by factory downtime. I have to prove we meet the regulatory requirements. So overall, how can my business deliver better client experience or better outcomes? For that, we need enablement through IoT. Okay. So the main components of an industrial IoT system are intelligent assets, devices, products, or a machine, and this can be of various kind. It can be a digital twin where you have a main factory and a digital twin of that, so that you can simulate results in the digital twin before they become effective in your data center. You can have data communication and infrastructure based on cloud and distributed computing. Analytics and software becomes very important. You need various kind of analytics to enable that, and of course you need people, processes, and systems. So this is the world reference model of IoT. So you have a lot of edge devices and they communicate a lot of information which comes into the center. And then so at the bottom, we have the physical devices and controllers, which are the Internet of Things. And they use the connectivity to provide edge computing so that from the edge devices, not every data needs to come to the center because that would have prohibitive communication costs. So you would do a lot of the computation at the edge, and then the data would be accumulated, and the important data, the key insights that you get would come to a central place where you can do various kind of analytics, various kind of visualization, and finally those can be utilized for collaboration and various kind of business processes. So this is the core structure of overall IoT process, IoT system, where the devices at the bottom gets the information and those get transformed into knowledge, which can be utilized for the business processes. Okay. So of course, the perceived benefits of IoT. So that is, there are lots of benefits from for IoT, from cost savings, from operational efficiency, to new, better streams of data to improve decision making, automated factory, automating business, new, better customer experiences, better visibility of the assets, and so on. So I think IoT is the way to go, and I think for Industrial 4.0, IoT will be a key component. But IoT cannot work on its own. It needs a lot of underlying technology. So the overall IoT market is really huge. And so if you look into our current internet and then we move to the IoT kind of consumer internet, and the scope of the business becomes almost twice as much. So it's a huge potential, and therefore a lot of companies like GE and others are embracing it totally. Okay. But what IoT brings with it is a lot of data. So each of these sensors, each of these machines will be generating a lot of data, and therefore the amount of data, as you can see, is processing in multiple ways. So currently we are in the area of social media, which we are all generating news, we are all generating photos, videos, and so on. So the data is going up. But now with the machines also generating data, you will enable a new area where the amount of data would be 4.3 zillion bits per minute with everything connected. And we have contextual customer experience. So big data becomes a key player in this age of the Industry 4.0 and IoT. Okay. So the coming flood of data. So by 2020, we have seen that the cloud video providers are providing data. Then we have the smart factories, connected airplane, autonomous vehicles, and the average internet users. So each of them are providing a lot of data. So unless we can, so the data becomes the key. Unless we can analyze the data in meaningful ways and get more value out of the data, companies that can make better use of the data, they will be the ones who will be successful. So the data explosions. So obviously we have started from megabyte to terabyte to petabyte to zettabyte, and now it is brontobyte. This would be our data in the near future, with the tons of data that are getting produced by these internet devices. Okay. And one of the key areas where this data would be produced are the sensors and actuators. So currently it is mostly humans and the human processes which were providing the data. But now with the sensors and actuators, it would be the machines which will produce the data, and the amount of data that is getting produced will explode. And so we are already we are seeing the location data using GPS sensors, and that is getting produced, data that are getting produced from the cameras and microphones, and now with various kind of sensory organs that can measure everything. So the amount of data would be multiple. So this data can come from multiple industries, multiple sources, from chemicals and gases to the temperature, to the position, presence, proximity, electronic data, magnetic data, and so on. So unless we can process this data well, analyze the data well, we cannot make meaning of the data, and we cannot do actual value out of this data. Okay. So the data value pyramid. So obviously the data at the bottom is just data, so which we collect, display, and plumb individual records. So that is the lowest form of data. So you obviously have the raw data, so that is not useful. So the first thing you can do is to collect this data. So the data can be collected in various ways. There are various tools that are available to collect data from multiple sources. But just getting this data, recording the data is not that useful, because that will just show some data in, for example, clean JSON format, but that may not be useful. So the next step is to do visualization. We clean, aggregate, and visualize this data using tools like Tableau. And so that is useful, so you can do the visualization, but just showing the visualization to a user may not be that useful, and therefore you need to provide reports on top of that. Based on the data, can you get some meaningful metadata out of that data, so that you can provide some structure to the data, tag the data that, okay, this is a visualization and this shows this anomaly in the data, so that you can make better use of the data. And so these reports would be useful, but then even more useful is to predict. So can you, based on the current data, can you predict the future? So for example, looking into the current data, can you predict in the future that this machine will go down, or you can predict that there is a threat coming based on the historical data? Can I do some predictive analytics to predict some data? And so that is the next step in the data value pyramid. And finally, based on the prediction, can you take some preventive action? You know that this machine will give a fault in within 1 day, so can you replace the machine? You know that a threat is coming, can you take some preventive measures so that the threat is minimized? So that is the data value pyramid, and this is one of the key areas of research and industrial potential, is how we can get meaningful analysis out of the thousands of data that is coming up, and go from the record to the chart to reports to prediction and finally to action. So this is the core of big data analytics, and a lot of companies from including IBM, which I'm part of, is trying to come up with new and better technologies for data analytics. Okay. So industrial big data analytics. So if you look at it, there is analytics, basic analytics, and if you look into the analytics and data, that is old answers to old questions. But if you now bring machine learning analytics, then it will answer new answers to old questions. And big data and machine learning analytics will open a new source, and it will allow us to get new answers to new questions. So that is the ultimate goal of big data analytics, that will utilize various analytics technique. It will utilize various AI techniques to make meaning out of thousands and thousands of petabytes of big data that comes from our industrial 4.0 IoT system. So that is the overall goal. Okay. So IoT data value chain. First is the data collection. So we, as I told before, that we have multiple of these devices that are spread all across the world. So what we need to do is to get this data collected in a meaningful way. So we have to get data from continuous generation from various IoT sensors, numerous distributed things, and transport to centralized location or do the processing at the edge itself. And that will lead to dynamic processing. So harvesting the data from multiple systems, converting to single usable format. So for example, different IoT devices may give you data in different formats. So unless you can convert the data to a single format which is usable, then only you can do meaningful analytics. So there are various kind of data formats that are coming up. JSON is becoming one of the standards that are used. So you try to utilize this kind of various kind of conversion tool, various kind of cleaning tool, so that you can clean out the data that is noisy, data that is not meaningful, so that you only get the usable data in a usable format. And then you need to understand and analyze the patterns of the data, so that you can say, okay, this is a trend forming, this looks to be an anomalous trend, this looks to be a useful pattern that is forming. So you understand the patterns, analyze the pattern, and utilizing that you gain meaningful insights out of the data. And once you have the insights, you need to now deliver. So for example, you can do some predictive analytics, and the ability to take action based on the insights that you gain, so you can predict the future, and then the ability to take action so that the anomalous events don't happen. And if you can successfully do that, the outcome would be optimized, predictable, and affordable, for example, electricity grid, efficient utility operations, and your customers will be satisfied by what you have been able to do by reducing the faults, eliminating major outbreaks, and so on. So this is the overall IoT data value chain that you need to aim for. And so for that, the big data analytics framework, so you need to go from the descriptive to the prescriptive. So obviously descriptive is looking into the data. So the data initially that will come will be totally raw. So there is not much usefulness out of that. So you will clean the data, remove the noise, and after that, looking at the data, you can say what has happened before. So you can give a description that, okay, your system has failed, for example, about 2 hours in the last 24 hours, or maybe that there was some error that was created in your system last day. These are the virtual machines that are taking up a lot of CPU space. So those are the descriptive analytics that looks at the data and says what happened. Obviously that is useful, but then the next questions come is why it happened. Why did my machine fail? Was it there was a problem in the hardware, or was there some software issues, or was the memory too full, and so on? So from the descriptive data analytics, you do the diagnostic, so that you can predict that why it happened, why was there a fault in my system, and for that, of course, you need more advanced analysis. And from the diagnostic, you move to the predictive. So in predictive, what you do, you can now look into the historical data and predict that, okay, if I see this kind of trend that is happening in my data, then I will know that there is a problem. And so therefore, if in the future, if the similar kind of trend happens, I can say, okay, this looks like a similar trend that I had seen 7 days back. So most probably there would be a fall that is coming up, and I can predict that. So if you can do the prediction, you can warn the people beforehand, that would be more useful. And finally, just not prediction, if you can now give some prescription, what action you need to take. So not only you can say that your machine will be rebooting in about 2 hours, you can take up some prescriptive action like, okay, maybe reduce these processes, increase the virtual memory that your system is using, so that the system won't go down. So this is the end-to-end spectrum of big data analytics, where you start from descriptive, where you just see what has happened, to go from descriptive to diagnostic, to say why it has happened. Then you move to predictive, and finally what you do, you go to a prescriptive mode, where you can say what action you can take, so that the system can automatically maintain itself. So that is the overall goal of an autonomous system, which can self-heal based on the tons of analytic data that you have and the analytics technique that you have created. So obviously, advanced analytics maturity path will follow this siloed approach, that you move from the descriptive to the prescriptive and finally to the cognitive analytics. So in descriptive analytics, it is insight. What has happened? So you looked into the files, the RDMS, and the data warehouse OLAP. So these were all systems which allowed you to find insight. It would allow you, after a system has failed, it would allow you to figure out what has happened, what was the problem, what happened to cause the problem. And from descriptive analytics, we have moved on to diagnostic analysis, which is, for example, enterprise data warehouse to in-memory databases, where you can do the diagnostic. You not only know what has happened, you can say why it has happened. So for example, there are various kind of BI tools that have been created, which can do event processing. It can look into the events to figure out that, okay, this problem happened because of this reason. And then it moved to predictive analytics, which is foresight. What will happen, when, and why? Okay, so this is where you try to use the newer techniques like NoSQL, mature in-memory database, and you have the data lakes created so that you can look into the historic data to predict the future. You look into the various historic data to see what was the trend that was there before a problem occurred, and based on that, you can say, okay, these are the problem that will happen again. And then, so after that, we move to prescriptive analytics, which is simulation-driven analytics and decision making and mature data lake. So here, what you will try to do is to not only say that this problem will happen, but you can also prescribe what action you can take to solve this problem. So in the context of, for example, the data center, then having a digital twin of the data center. So maybe you have a digital twin of the data center where you will say that, okay, let me do this simulation. And if that is solving the problem, maybe that is the prescription that I will give, that, okay, do this action and then the problem will not happen. And finally, the ultimate goal is to obviously take advantage of artificial intelligence, machine and deep learning framework, so that you can have a self-learning and completely autonomous enterprise. So that the systems itself will, without human intervention, will know, okay, this is a problem that may happen, and this is the action I will take so that this problem goes away. And then the human intervention will be very low, and the downtime of the system would be very low, and you will have all that you need. So that would be the overall analytics goal. So obviously, there are a lot of systems that are getting developed from the descriptive analytics. We had various kind of databases to diagnostic analytics. We have visualization tools like Tableau, to now various companies like Splunk and others are coming up with predictive analytics technique. And obviously, going forward, I think there are a lot of scope of cognitive analytics where you utilize deep learning and machine learning in an effective way to solve this analytics problem. So the question then becomes is, we have talked about IoT and we have talked about analytics. So, but then the question that comes up is, how will all these systems come together? You have the, as we had talked before, we had shown you the overall IoT reference architecture, where you had the sensors at the bottom, then the edge computing, and finally the central processing event. So the question that comes up for academicians, researchers is, okay, so I want to create an end-to-end IoT system. So one of the great things that has happened in recent past is that the public cloud forums like AWS, Amazon, IBM Cloud, Microsoft Azure, Google Cloud, they are providing you a end-to-end architecture for IoT, where they provide various kind of SDK, which allows you to collect data from multiple sensors, and then they provide various kind of tools and techniques so that you can utilize the end-to-end public cloud forum to do the analytics. So for example, in the AWS world, they have a overall IoT architecture, where they have various kind of rule engines for doing various kind of processing. They have the message brokers so that different kind of protocols can be communicated, and so on. They provide the AWS IoT application SDK, which can be used for creating AWS IoT applications, and then the various things, the various devices, you can get the data from those devices, firstly into an edge location and finally into the central location. And then AWS provides various kind of tools. So for example, Amazon S3 can be used for storing the data. Amazon Elasticsearch can be used for doing the basic ELK based search of the data. CloudWatch can be used for monitoring, and then you can use AWS Lambda to do various kind of serverless programming on the site. So this provides various public. So it's just like AWS provides the IoT architecture, similar kind of architecture is provided by the public clouds, like the Azure has a similar kind of structure, Google Cloud has similar kind of structure. So the question for the academicians, for the researchers is which cloud to choose. So the answer is multi-cloud. You do not restrict yourself to one public cloud. You do various kind of, depending on which function that you want to use, you use different clouds. You maybe use AWS for some work, you use Azure for some other work, then use Google for some other work. And maybe if the data is very sensitive, you do not even utilize the public cloud. You use a private cloud in your own data center using VMware technologies. So more and more, the future that is coming up is a hybrid multi-cloud platform, where you will have a system based on a multiple cloud. You will have some of your data in Google, some of your data in Azure. Then you will have a central place where maybe some of your key data, which is very sensitive, which you don't want to provide exposed to the public cloud, you put it in the central data framework. And we are saying IBM, what we are trying to work out is multi-cloud analytics framework, multi-cloud management framework, where we will get your data from the multiple sources, and then we will have a central logging and a central processing place where we can do various kind of insights and analytics. So looking into this picture, which shows our high-level architecture of this multi-cloud analytics framework. So the customer data can be in Azure Monitor. The customer data can be at Azure, and we can use Azure Monitor to get the key insights into a central processing unit. Obviously, we do not want to have all the data from the public cloud into the central base, because then the data communication cost would be prohibitive, but we will get only the key insights into our central processing side. Similarly, from Amazon, we can get data from Amazon CloudWatch, or we can do some actual searching inside Amazon itself and create a Elasticsearch framework within Amazon and get the key insights to our central location. And similarly, we can get data from the Google Cloud. And internally in our centralized procession, what we can do cross-cloud insights and analytics using our own centralized Elk stack. We have Elasticsearch, Logstash, and Kibana for the visualization. And so once we maybe some of the insights that are there in Azure, in Amazon, you may get some other kind of insights. Google Cloud will provide you some other insights. So this multi-cloud analytics with a centralized dashboard that will provide you with the best of all the worlds. You can do analytics at the public cloud itself, take advantage of what are the good features of the different public clouds, but then also you can provide in key insights based on this overall multi-cloud analytics framework. So we believe that going forward, so this would be a key way that companies need to operate to take full advantage of the industry 4.0. They need to have the various kind of edge devices that are providing data. You do a lot of analytics in the edge, and you can have a similar kind of multi-cloud analytics framework at the edge also, or you can have data from the edge getting moved to the central location. And then you can have an overall multi-cloud analytics, multi-cloud insights framework that will give you deep understanding of the overall data, and that can help you to create a autonomous system that makes good best advantage of your overall power. So in conclusion, what we believe that Industry 4.0 is critical for competitive advantage and survival in not so distant future. IoT are the backbone of building disruptive organization and smart factories. An organization need to rise up the maturity level of IoT by utilizing other kind of technologies like analytics and cloud computing for true leverage of all the disruptive technologies. So that in the nutshell is our thoughts in IBM on how to take advantage of the Industry 4.0 by making use of the related technologies like IoT, analytics, and cloud computing. I will stop here and I can answer any questions if there are any questions. Thanks.
Thank you, sir. Thank you for giving a great lecture on the recent developments in industrial IoT and industrial big data analytics. Over to the audience. So there is one question from the audience side. Can you please give an example of new questions and new answers brought by ML analytics to big data?
Give an example of new question. So I think so one of the key things that ML analytics will bring to big data is the predictive part. So far what has happened is that we have looked into the data and we can answer things from the future. And what we can also do is to say that, okay, why has this fault happened? So we have so far most of the system have been only descriptive, but the prediction part, the predictive analytics is something that is being enabled by machine learning, because what we can do utilizing machine learning and combining the historical data with machine learning is to predict the future. So that I think predictive analytics is still at infancy. There are very few commercial systems which can truly do good predictive analytics. So going forward, I think machine learning will make this predictive analytics really mature and enable us to answer questions even before that has happened. And that will be really helpful going forward. So the next question is edge as a service versus IoT. I think both are needed because edge, I think the IoT devices can be spread across a multiple area, and what we need to do is to get all those data from the IoT to the edge part. So sometimes the data may be start from the edge, but sometimes the data may be spread further out in the IoT space. And so as I showed in the IoT reference model, the edge has a space, but I think the IoT will be even below the edge. It will get data from the multiple sensors, which may be even further spread out, and then it will come to the edge, which will do some further processing before it moves to the central location.
Yes, sir. Any more questions? One more question. Edge replaced by everything then?
Yeah, edge is replaced by everything. So I think so. I think edge computing has a really so the maturity model of edge computing. So that is, I think, one of the key areas that is there for research. And we have come a long way in cloud computing, where we have, but there the cloud computing is only. So, for example, if you look into the major cloud providers like AWS and Azure, they are spread. Their data centers are spread only in a very few places. But I think as we go forward, moving to the edge will become the key, because obviously as the data grows, the data communication is becoming very important. But I think if we have to move all the data to every place, that will make it very cost ineffective for the companies. So doing a lot of the work in the edge, and then finally moving only the key insights to central processing is a key part that is needed. And therefore edge computing, I think, should be a key place and going forward.
Yes, sir. One more question from the person.
Yeah, I am praising AWS because so IBM, obviously we have our own cloud, and that cloud is also very cost effective. And the other part we also have is we have Red Hat, which is one of the key acquisitions that we had from last year. And that obviously is a key element. OpenShift of Red Hat is a key element of private cloud. But we believe in, especially in IBM services, we believe that the future is multi-cloud. We cannot restrict the company to only focus on AWS or Azure or Google. We, depending on the customer, they need to be going to all the clouds, because each cloud will provide the benefit. And the ultimate key would be providing a multi-cloud, hybrid multi-cloud kind of framework. And for that, we recognize that companies will utilize multiple cloud, and we want to provide a service on top of that that encompasses all the clouds.
Sir. More questions?
Okay, thanks everyone. Thanks for the insightful questions. And if you have any further questions or want to discuss further, I'm always available. You can contact me on LinkedIn or connect me on my email. I'll be happy to answer and talk more about what we are doing in IBM in this space. Thanks a lot.
Thank you, sir, for that wonderful session and interactive question and answer session. Thank you, sir.
Thanks.
This, we have come to the end of the two-day summit, DX21 Digital Transformation Summit. On behalf of ACM Trivandrum chapter and the entire team of Kerala University of Digital Sciences, Innovation and Technology, KUDSIT, and on my personal behalf, I extend my sincere thanks to all the speakers who have accepted our invitation and joined us online for sharing their ideas and discuss the recent developments in the area. I also thank all the participants who have attended the summit. Hope all of you had a wonderful session on these 2 days. I would also like to express my sincere thanks to Dr. Saji Gopinath, Vice Chancellor, Kerala University of Digital Sciences, Innovation and Technology, for his immense support in conducting this summit. I also extend my sincere gratitude to KDISC, IEEE ComSoft, and GTech for the immense support in organizing this event. I would also like to place my immense gratitude to the ACM Trivandrum chapter and to Professors Ashraf and Dr. Sabu M. Thambi for their perfect logistic support and guidance they have extended to all of us in organizing this summit. Thank you, sir. Again, I thank the KBA team for the technical support they have offered us on these 2 days. And last but not the least, I extend my sincere thanks to all the faculty members, staff, and my friends at Kudsit for their enormous cooperation in organizing this event and for the successful completion of this event. Thank you all again.